Look up at the night sky. You see a vast, silent ocean of black, punctuated by the brilliant, steady light of distant suns. It feels immense, almost infinite. But what if I told you that this breathtaking vista, this entire cosmos we can observe with our most powerful telescopes, might just be the surface? What if reality is like an onion, and we've only just begun to peel back the very first layer? For centuries, we've believed that the universe is composed of the things we can see and touch: planets, stars, galaxies, the fabric of space and time itself. Yet, a growing chorus of the world's most brilliant physicists and cosmologists are now proposing an idea so radical it challenges the very foundation of our existence. They suggest that our universe, in all its splendor and scale, might be merely one layer of a far grander, multidimensional reality. There could be entire worlds, forces, and perhaps even other versions of ourselves existing just a whisper away, completely hidden from our senses and our finest instruments. This is not science fiction. This is the cutting edge of scientific inquiry, a frontier where mathematics and imagination collide. Today, we embark on a journey to the very edge of known physics, to explore 30 of the most fascinating, mind-bending theories about the universe's hidden layers. We will venture from the well-established pillars of theoretical physics to the wildly speculative realms that border on philosophy. We will investigate the possibility of tiny, curled-up dimensions woven into the fabric of space itself, so small that they escape all detection. We will confront the notion that our three-dimensional universe might be a holographic projection from a two-dimensional surface at the edge of reality. We will even entertain the breathtaking idea of a multiverse, an endless cosmic froth where every possible outcome of every possible event unfolds in its own separate bubble of space-time. Each theory is a key, an attempt to unlock a door to a deeper understanding of why the universe is the way it is. This exploration is more than just a list of ideas. It is an invitation to experience the wonder and intellectual curiosity that drives humanity's greatest quest for knowledge. It is a journey that asks you to set aside what you think you know and to consider possibilities that defy easy imagination. We are about to dive into concepts that explain the deepest mysteries, from the nature of dark matter and dark energy to the very origin of the Big Bang. So prepare to have your perception of reality stretched, twisted, and fundamentally reshaped. This is a voyage into the hidden architecture of everything, and what we discover there might just change everything we thought we knew about our place in the cosmos. Our journey into the hidden layers of reality begins with what is perhaps the most staggering proposition of all, that our universe is not alone. We start with the Level 1 multiverse, a concept that flows directly from our leading scientific theory of the cosmos's origin. You see, the Big Bang wasn't just a single, explosive event in the distant past. According to the theory of cosmic inflation, the very beginning of our universe was marked by a period of fantastically rapid expansion, where space itself stretched faster than the speed of light. But here's the truly mind-bending part. This inflationary process might not have been a one-time affair. For most of the cosmos, this hyper-expansion may never have stopped. This is the idea of eternal inflation. Picture an infinite pot of water that is forever boiling. Every now and then, in a certain spot, the boiling stops. That cessation of violent activity allows a stable bubble to form. In our cosmic analogy, that bubble is a universe like our own, where inflation has ended and normal, slower expansion takes over, allowing for galaxies, stars, and planets to form. But outside our bubble, the frantic boiling of inflation continues unabated, constantly giving birth to new, separate bubble universes. This process is eternal, creating an endless, frothing ocean of cosmic bubbles, a vast foam of realities. Our entire observable universe, with its hundreds of billions of galaxies, is just one single bubble in this unimaginably vast cosmic array. Think of it as a gigantic, infinitely rising loaf of raisin bread. Each raisin represents a galaxy. As the dough rises, the raisins move apart from each other. Now, imagine that the dough is rising so incredibly fast that pockets of it solidify into their own distinct loaves, each with their own set of raisins, completely isolated from one another. We live in one of those loaves, utterly unaware of the countless other loaves being created all around us. What makes this theory so compelling is that it isn't just wild speculation. It emerges naturally from the mathematics of inflation. If inflation is possible and if it's eternal, then an infinite multiverse isn't just likely, it's inevitable. And this leads to an even more profound implication. In an infinite array of bubble universes, the fundamental constants of nature, the strength of gravity, the mass of an electron, the very number of spatial dimensions, might be determined randomly when each bubble forms. In some bubbles, gravity might be so strong that universes collapse instantly. In others, the forces might be too weak for atoms to ever form. But in a rare few, like ours, the numbers are just right for stars, planets, and life to emerge. This multiverse could be the ultimate explanation for the puzzling fine-tuning we observe in our own cosmic home. And yet, the cosmic raisin bread of the Level 1 multiverse might only be the beginning. If we venture even deeper into theoretical territory, we encounter a second, even more exotic layer of reality. This is the Level 2 multiverse, and it emerges not from the expansion of space itself, but from the mind-bending principles of string theory. You see, for string theory to work mathematically, it requires our universe to have more than just the three spatial dimensions we experience: length, width, and height. The theory suggests there are actually 6 or 7 extra spatial dimensions, but they are curled up or compactified into shapes so incredibly tiny that they are far, far smaller than a single atom. But here is where the plot thickens enormously. It turns out there isn't just one way for these extra dimensions to curl up. In fact, the number of possible stable configurations is so astronomically large it defies any meaningful analogy. Physicists call this vast collection of possibilities the string theory landscape, and the number of potential universes within it is estimated to be around 10 to the power of 500. To grasp the sheer scale of that number, consider that the total number of atoms in our entire observable universe is only about 10 to the power of 80. This landscape is, for all practical purposes, infinite in its variety. Each point in this landscape represents a unique way for the extra dimensions to be folded. And each unique fold has profound consequences. The specific geometry of these hidden dimensions dictates the fundamental laws of physics in the universe they create. They determine the strength of gravity, the masses of elementary particles, the number of forces, and even the number of dimensions we perceive as large. In one fold, gravity might be 1 billion times stronger, leading to a universe that collapses in a fraction of a second. In another, electromagnetism might be too weak to hold atoms together, preventing chemistry and life from ever getting started. Our universe, then, is not special because its laws are uniquely destined. It is simply one specific point in this gargantuan landscape, a place where the random dice roll of dimensional folding resulted in a set of constants that allow for galaxies, planets, and conscious beings like us to exist. This is often called the Anthropic Principle in its weakest form. If the universe weren't fine-tuned for life, we wouldn't be here to observe it. What makes the Level 2 multiverse distinct from the Level 1 version is the nature of the separation. In the inflationary bubble multiverse, all the universes share the same fundamental laws of physics deep down. They just have different initial conditions and perhaps different random outcomes for the constants. But in the string theory landscape, the universes can have genuinely different laws. They are not bubbles floating in a larger, inflating space. Instead, they are more like separate, disconnected islands in a vast cosmic archipelago, each with its own distinct physical constitution. The journey between them would be impossible, as it would require rewriting the very rulebook of reality. This theory provides a potential, albeit highly speculative, framework for answering one of cosmology's biggest questions: why does our universe seem so perfectly tailored for life? The answer, according to this view, is that we are simply looking at the problem from the wrong angle. There is no why in the sense of a grand design. Instead, every possible universe exists somewhere in the landscape, and we, by necessity, find ourselves in one of the exceedingly rare ones that can support our existence. It is a cosmic version of finding a needle in a haystack, but where the haystack is so incomprehensibly vast that finding a needle becomes a statistical certainty. But if you thought the cosmic bubbles of level 1 or the disconnected islands of level 2 were staggering, prepare yourself for a theory that strikes at the very heart of reality and our place within it. This is the level 3 multiverse, born not from cosmology but from the bizarre and counterintuitive world of quantum mechanics. At the subatomic level, the universe doesn't operate with the certainty we experience in our everyday lives. Particles exist in a haze of probability, a superposition of all possible states, until the moment they are observed or measured. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until someone looks inside. The conventional explanation, the Copenhagen interpretation, says that the act of observation forces the particle, or the cat, to choose a single state, collapsing the probability wave into one reality. But an alternative view, proposed by Hugh Everett in the 1950s, offers a radically different and, for many, a more elegant solution. It's called the many worlds interpretation, and it suggests that the wave function never collapses at all. Instead, every time a quantum event occurs with more than one possible outcome, the entire universe splits. Every probability is realized, but in a newly branched parallel reality. In one branch, the radioactive atom in Schrödinger's box decays and the cat dies. In the other, perfectly real branch, the atom does not decay and the cat lives. There is no collapse, just a continual, unending divergence of reality into a mind-numbingly vast tree of possibilities. And this isn't just for carefully constructed laboratory experiments. It happens constantly at every moment for every quantum particle everywhere. Every time an electron changes its orbit, every time a photon reflects off a surface, every random quantum fluctuation is a fork in the road, creating new universes that encompass every single possible outcome. What distinguishes the Level 3 multiverse from the others is its intimate connection to our own reality. The Level 1 bubbles are far away in space, separated by unimaginable distances in an ever-inflating cosmos. The Level 2 islands from string theory exist in a disconnected landscape with different physical laws, but the branches of the many worlds interpretation are all part of the same underlying quantum wave function and the same space-time continuum. They are not elsewhere in space, they are right here, superimposed upon us, but separated by a different kind of distance, a quantum decoherence that prevents any communication or interaction between the branches. Think of reality as an endlessly branching river. We are like a leaf floating down one specific current. We can only experience the path we are on, but at every rock, every eddy, the river splits and other versions of us flow down countless other channels. In one branch, you decided to click on this video. In another, almost identical branch, you scrolled past. In one reality, a historical event unfolded exactly as we record it. In another, the outcome was different. Every choice you've ever made and every choice you didn't make has been made by a version of you in a parallel world. The implications are quite literally infinite. There is a universe where you are a famous musician, another where you pursued a different career entirely, and countless more with variations so subtle you would never notice the difference. This perspective solves the thorny philosophical problem of what constitutes an observation that collapses the wave function. In the many worlds view, there is no special role for consciousness. The universe and everything in it, including us, are part of the quantum system, constantly branching. While this idea can feel deeply unsettling, as it seemingly diminishes our unique existence, it also presents a universe of immense and unending possibility, where every story that can be told is being told somewhere in the sprawling tapestry of quantum reality. Yet, for all its grandeur, the many worlds interpretation still operates within a familiar framework of space and time. But what if even that framework is an illusion? Our fourth theory takes us to the precipice of a concept so profound it challenges the very nature of dimensionality itself. This is the holographic principle, an idea that suggests our experienced reality, with its rich three-dimensional depth, might be nothing more than a projection, a cosmic hologram. The roots of this astonishing notion don't come from science fiction, but from one of the most perplexing puzzles in physics, the information paradox of black holes. When an object falls into a black hole, according to Einstein's general relativity, it is lost forever, its information seemingly vanishing from the universe, which violates a fundamental tenet of quantum mechanics that information can never be destroyed. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, a measure of its hidden information or disorder, is not proportional to its volume as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the point of no return. It was as if all the information about everything that had ever fallen into the black hole was somehow encoded on its two-dimensional boundary. This revelation was developed further by Gerard T. Hooft and Leonard Susskind, who proposed a radical solution. They suggested that the information isn't lost inside the black hole because it was never actually in the volume to begin with. It was always stored on the surface. In essence, the three-dimensional interior of the black hole is a projection of the information encoded on its two-dimensional boundary, much like a hologram. In an ordinary hologram, a two-dimensional film contains all the information needed to project a seemingly three-dimensional image. Shine a laser on it and a full, deep image appears. The holographic principle boldly applies this concept to the entire universe. It posits that our reality, with all its galaxies, stars, planets, and even us, might be a vast and incredibly complex holographic projection. All the information that describes everything happening in our three-dimensional cosmos could be encoded on a remote, two-dimensional surface that surrounds us, the cosmological horizon at the edge of the observable universe. We are, in a very real sense, living inside a projection. This is more than just a clever analogy. It's a potential framework for solving the greatest problem in theoretical physics, uniting Einstein's theory of gravity, which describes the large-scale structure of spacetime, with quantum mechanics, which describes the microscopic world of particles. Gravity is the force that shapes the cosmos, but it has stubbornly resisted all attempts to be described in quantum terms. The holographic principle offers a breathtakingly elegant solution. It suggests that gravity itself is not a fundamental force in the way we think. In the higher dimensional, bulk reality, gravity emerges as a consequence of the quantum interactions happening on the lower dimensional boundary. Think of it like watching a movie on a screen. The intense three-dimensional drama you see, the explosions, the emotions, the sweeping landscapes, is all an illusion created by the interplay of light and color on a flat, two-dimensional surface. In the same way, the force of gravity we feel and the curvature of spacetime we inhabit might be emergent properties, a direct consequence of the complex quantum information processing occurring on the universe's two-dimensional boundary. This holographic duality implies that a theory without gravity in a lower dimensional space can be mathematically equivalent to a theory that includes gravity in a higher dimensional space. For physicists, this is a powerful tool, allowing them to translate intractable problems in quantum gravity into more manageable problems in quantum field theory. The holographic principle doesn't just suggest hidden layers to reality. It implies that the reality we perceive is the secondary effect, a shadow cast by a deeper, simpler, and perhaps more fundamental two-dimensional reality. Moving from the idea that our reality might be a projected illusion, we now encounter a theory that reimagines the very stage upon which the cosmos unfolds. This is the concept of brain cosmology, a framework that emerges from string theory and paints a picture of our universe not as an isolated island, but as one structure floating within a much larger, higher-dimensional reality. The word brain is simply a short form for membrane. In this view, the three spatial dimensions we know and love, the length, width, and height of our everyday experience, might constitute just one three-dimensional brain. But this brain of ours is not floating in nothingness. It exists within a grander, higher-dimensional arena known as the bulk. This bulk space could have 4, 5, or even more spatial dimensions that are completely inaccessible to us, much like a character living on a single page of a book would be utterly unaware of the other pages above and below it. We are confined to our brain, unable to perceive or move into the bulk dimensions, but other brains could be floating out there, parallel to our own, each potentially hosting its own entire universe with different physical laws. One of the most dramatic models within this framework is the ekpyrotic universe scenario. The name comes from the Greek word for conflagration or fire, and it offers a powerful alternative to the standard inflationary Big Bang theory. Instead of a singularity, a point of infinite density and temperature, the ekpyrotic model proposes that our universe's hot, dense beginning was the result of a colossal collision. Picture two immense, perfectly flat, three-dimensional brains moving slowly toward each other through the hidden higher-dimensional bulk. They are parallel to one another, separated by a tiny gap in this extra dimension. When they finally meet, the impact releases an enormous amount of energy, heating our brain to an incredible temperature and filling it with the raw material of particles and radiation. This violent, transformative event is what we now call the Big Bang. It wasn't the beginning of space and time, but rather a dramatic phase transition, a rebirth of our cosmic environment triggered by an encounter with another world. A simple, if slightly whimsical, analogy can help make this abstract idea more tangible. Imagine the higher dimensional bulk as a giant, cosmic loaf of bread. Now think of our universe as just one slice of that bread, a flat, three-dimensional brain. Somewhere else in the loaf, there is another slice, another brain floating parallel to ours. For most of time, these two slices are far apart, but then the loaf is compressed, or perhaps the slices simply drift together. They collide. The moment they smack into each other, the energy of that impact spreads across the surface of our slice, like the heat and vibration you'd feel if you slapped two pieces of bread together. That energy and agitation reverberating across our three-dimensional brain is what created the initial hot, dense state from which our entire observable universe expanded and cooled. In this view, the Big Bang was not a unique creation event from nothing, but a cyclical occurrence. The brains could bounce apart after the collision, eventually drifting back together for another cosmic collision, potentially creating an endless cycle of universal death and rebirth. This theory presents a compelling rival to the dominant theory of cosmic inflation. While inflation explains the universe's large-scale uniformity by proposing a period of fantastically rapid stretching, the ekpyrotic model achieves a similar outcome through a different mechanism. The slow, gradual attraction of the brains before the collision naturally smooths and flattens the universe, erasing any previous irregularities. It's like slowly pressing two wrinkled sheets of paper together. The pressure forces them to become flat and uniform where they contact. This process can explain why our cosmos appears so homogeneous on the largest scales without requiring a brief era of hyper-expansion. Furthermore, brain cosmology offers a potential explanation for one of the universe's greatest mysteries, the nature of gravity. Why is gravity so unimaginably weaker than the other fundamental forces? The proposal is that while electromagnetism and the nuclear forces are confined to our brain, gravity is different. It is a force that can leak out, spreading its influence into the extra dimensions of the bulk. This dilution of gravitational force across a larger spatial volume would explain why it feels so feeble to us, trapped here on our three-dimensional membrane. Now, as we move from the grand cosmic architecture of brains and holograms, we turn our attention inward to the very fabric of matter and energy. Our sixth theory, supersymmetry, or SUSY for short, proposes a profound and elegant hidden layer woven directly into the quantum realm. This is not about extra dimensions or parallel worlds, but about a deep, fundamental symmetry that, if it exists, would revolutionize our understanding of the particle zoo. You see, the standard model of particle physics has been a triumph of human ingenuity, brilliantly cataloging the elementary particles that make up everything we see. But for all its success, physicists have long felt it's incomplete, a bit like a beautiful puzzle with a few pieces that don't quite fit. Supersymmetry is the proposal for those missing pieces, a symmetry so powerful it would create a perfect partnership between the two great families of particles. In one family, we have the fermions. These are the particles of matter, the building blocks of stuff itself. Think of electrons orbiting an atom's nucleus and the quarks that make up the protons and neutrons inside that nucleus. They are the ultimate Lego bricks of material reality. In the other family, we have the bosons. These are the particles of force, the messengers that carry nature's fundamental interactions. The photon is the boson for electromagnetism. Gluons carry the strong nuclear force that holds atomic nuclei together, and the W and Z bosons mediate the weak nuclear force responsible for radioactive decay. For decades, these two families have lived in the same model but under very different rules. Supersymmetry proposes a breathtakingly simple and beautiful solution. For every known fermion, there should be a bosonic superpartner, and for every known boson, a fermionic superpartner. It's a cosmic pairing, a fundamental kinship between matter and force. This means the electron, a fermion, would have a bosonic partner called the selectron. Each type of quark would have a corresponding squark. On the other side, the photon, a boson, would be paired with a fermionic partner called the photino. The gluon would have a gluino. This doubles the number of elementary particles in an instant, creating a hidden world of superpartners just waiting to be discovered. But why would nature require such duplication? The answer lies in solving some of the most nagging problems in modern physics. The first is known as the hierarchy problem. This is the puzzle of why gravity is so absurdly weak compared to the other forces. The electromagnetic force, for instance, is about 10 to the power of 36 times stronger than gravity. That's a 1 with 36 zeros after it. To appreciate that disparity, it's the difference between the strength of a single magnet holding a paperclip to your fridge and the gravitational pull of the entire planet Earth. In the standard model, this vast difference is incredibly unstable. Quantum corrections, tiny fluctuations in the energy fields, should naturally drive the mass of the Higgs boson, and by extension, the scale of the weak force up to a value quadrillions of times larger, effectively making our universe impossible. It's as if you're trying to balance a pencil perfectly on its point. The slightest breath of air should knock it over, yet somehow it remains standing. Supersymmetry provides a stunningly elegant fix. It proposes that the quantum contributions from the known particles are perfectly cancelled out by the contributions from their superpartners. It's a natural, built-in cancellation mechanism that stabilizes this delicate balance, making a universe like ours not just a fluke, but a natural outcome of a more symmetric law. Furthermore, supersymmetry offers a compelling candidate for the identity of dark matter, that mysterious, invisible substance that makes up about 85% of the matter in the universe. The lightest supersymmetric particle, or LSP, is theorized to be stable and not interact with light, making it a perfect fit for the profile of dark matter. In many models, this particle is the neutralino, a mix of the superpartners of the photon, the Z boson, and the Higgs. If this is correct, then supersymmetry wouldn't just be an abstract mathematical curiosity. It would explain the very glue that holds galaxies together. The hunt for these superpartners has been one of the primary missions of the world's most powerful machine, the Large Hadron Collider, or LHC. The idea is that by smashing protons together at velocities approaching the speed of light, we can recreate the energetic conditions of the early universe. If supersymmetry is a law of nature, these collisions should occasionally produce superpartner particles. The catch is that these particles are expected to be very heavy, which is why we haven't seen them in lower energy experiments. They would be unstable and almost instantly decay into the lighter particles we know, leaving behind a unique signature in the detectors, an imbalance of momentum or specific combinations of jets and leptons that physicists meticulously search for. So far, the LHC has not found definitive evidence for supersymmetry, which has pushed the possible mass range for these particles higher than many theorists had hoped. This has led to some tension within the physics community. Has nature chosen a different path to solve these problems, or are the superpartners simply heavier than we anticipated, waiting for even more powerful colliders to reveal them? The search continues because the payoff, the discovery of this profound hidden symmetry, would be one of the greatest achievements in the history of science. But what if the hidden layers of reality are not a product of nature, but of technology? This brings us to one of the most provocative and widely debated ideas of the 21st century, the simulation hypothesis. This theory dares to suggest that our universe, with all its complexity, beauty, and pain, might not be the fundamental level of existence. Instead, it could be an artificial construct, a kind of hyper-advanced computational simulation, not unlike a video game created by a vastly more intelligent civilization. While it sounds like the plot of a science fiction film, this concept is taken seriously by a number of prominent philosophers, scientists, and technologists who argue that it is not only possible but, under certain assumptions, even probable. The most famous articulation of this idea comes from the philosopher Nick Bostrom. His argument is structured around a simple but powerful trilemma, a set of three possibilities, at least one of which must be true. The first possibility is that almost every civilization like ours goes extinct before reaching a post-human stage, a level of technological maturity where it could create realistic simulations of conscious beings. The second possibility is that if a civilization does reach that post-human stage, almost none of them would have any interest in running such simulations, perhaps for ethical reasons or simply a lack of curiosity. The third and final possibility is that we are almost certainly living in a simulation right now. Bostrom's logic is statistical. If even a tiny fraction of advanced civilizations survive, and a tiny fraction of those decide to run ancestor simulations, perhaps for scientific research, entertainment, or historical preservation, then the number of simulated minds would quickly and vastly outnumber the one original biological population. The odds that you or I are one of the original, base reality beings would be astronomically small. We would, by the sheer law of large numbers, almost certainly be simulated entities. This line of reasoning forces us to confront some truly mind-bending implications. If our reality is a simulation, then the laws of physics we have so painstakingly uncovered are not fundamental laws of nature. They are the programmed rules of the simulation, the underlying source code of the universe. This perspective can cast some of the strangest aspects of quantum mechanics in a new light. For instance, the observer effect, where a particle seems to exist in multiple states until it is measured, could be seen as a clever programming optimization. Why render the entire universe in perfect detail all the time? It would be far more efficient for the simulation to only generate high-resolution detail when and where it is being observed, much like a video game only renders the graphics on the part of the map the player is currently viewing. The finite speed of light could be interpreted as a processing speed limit for the cosmic computer. Even the seemingly fundamental, indivisible quanta of energy and space could be seen as evidence of a pixelated reality, a cosmic resolution limit. However, many physicists push back strongly against this interpretation. They argue that finding our universe to be mathematically consistent and computable is not evidence that it is a computation. It's evidence that we are developing better models to describe it. The fact that we can simulate quantum phenomena on our own computers doesn't mean the universe is a simulation. It means our computers are powerful enough to mimic a small part of its behavior. Furthermore, if the simulation is so perfect that it's indistinguishable from base reality, the question may be functionally meaningless. Whether we are made of stardust or lines of code, our experience of love, loss, curiosity, and wonder remains just as real to us. The simulation hypothesis ultimately lies in a strange space between science and philosophy. It is notoriously difficult, if not impossible, to test scientifically. Any evidence we might find for it could simply be part of the simulation's design. Yet, it remains a powerful thought experiment that challenges our deepest assumptions about existence, consciousness, and our place in the cosmos. It asks us to consider that the ultimate hidden layer might not be a deeper dimension or a parallel world, but the cold, sleek hardware of a computer belonging to a being we could never comprehend. Now, from the speculative realms of simulated realities, we return to a cornerstone of modern cosmology, a theory that is both more established and, in its own way, just as profound. This is cosmic inflation, a concept that doesn't just add a hidden layer to reality, but describes the very mechanism that set the stage for everything that followed. The standard Big Bang model, for all its success, was plagued by a few very stubborn puzzles. The first is known as the horizon problem. If you look at the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, you find something remarkable. It is almost perfectly uniform in temperature. No matter which direction you point your telescope, the temperature is the same to within 1 part in 100,000. This creates a serious issue. In the standard model, these distant regions of the universe were never close enough to interact and smooth out their temperature differences. They were, in cosmological terms, beyond each other's horizon. It would be like walking into a vast, crowded room and finding that every single person, even those on opposite sides who have never met, is wearing clothes of the exact same color and style without any prior coordination. How could such perfect uniformity have been established? The second major issue is the flatness problem. Our universe appears to be incredibly flat on the largest scales. This isn't flat like a table, but flat in a geometric sense, meaning that the fabric of spacetime is not curved on a cosmic scale. The density of matter and energy is incredibly fine-tuned to a critical value that allows for this flatness. In the standard Big Bang, any tiny deviation from this perfect flatness in the early universe would have been magnified exponentially over billions of years. For our universe to be as flat as we observe it today, its initial conditions had to be fine-tuned to an astonishing degree of precision, like balancing a pencil on its point for 14 billion years without it ever falling over. This level of fine-tuning seemed unnaturally coincidental. Cosmic inflation, proposed by Alan Guth and others in the early 1980s, solves both of these problems in one elegant sweep. The theory posits that a tiny fraction of a second after the universe's birth, around 10 to the power of -36 seconds, it was seized by a peculiar kind of energy that caused it to expand at a staggering exponential rate. For a fleeting moment, the universe doubled in size every tiny fraction of a second, inflating by a factor of at least 10 to the power of 78. To grasp that scale, imagine a single atom suddenly swelling to the size of our entire observable universe, all in an infinitesimal blink of an eye. This period of hyper-expansion is the hidden layer that determined the initial conditions of our entire cosmic history. This incredible stretching action solves the horizon problem effortlessly. Before inflation, the entire observable universe was crammed into a volume much smaller than an atom. This tiny region was small enough for every part to be in causal contact, allowing it to reach a uniform temperature, just like a small cup of coffee will naturally cool to a single, even temperature. Then, inflation took this tiny, homogeneous patch and stretched it to a size larger than our entire visible cosmos. The regions that appear causally disconnected today were once intimately connected in that primordial speck. The perfect uniformity we see is simply a relic of that initial pre-inflationary equilibrium. Inflation also naturally explains the flatness problem. Think of the surface of a balloon. When it's small, you can easily see its curvature. But if you inflate that balloon to an absolutely colossal size, the small patch of its surface that you can see from your vantage point will appear perfectly flat. In the same way, the violent stretching of inflation took whatever the initial curvature of our universe was and flattened it out, just as stretching any flexible surface makes a small section of it appear flat. Our universe isn't perfectly flat by cosmic accident. It's flat because the inflationary process ironed out any primordial wrinkles, leaving behind the smooth, geometric landscape we observe. But what was the engine of this incredible expansion? The leading candidate is a hypothetical field that permeated the early universe, known as the inflaton field. Think of a field as an invisible entity that exists throughout space, much like a magnetic field, but with its own unique properties. The inflaton field found itself in a peculiar state called a false vacuum, a high-energy condition that exerted a powerful negative pressure, causing spacetime to expand at an accelerating rate. As this field slowly relaxed or rolled down to its true lowest energy vacuum state, the energy stored within it was released, reheating the universe and filling it with the hot plasma of particles that would eventually form atoms, stars, and galaxies. This transition marked the end of inflation and the beginning of the more sedate, hot Big Bang expansion we are familiar with. The most spectacular consequence of inflation, however, is not just the smoothness it creates, but the tiny imperfections it leaves behind. According to quantum mechanics, empty space is never truly empty. It is a seething foam of virtual particles constantly popping in and out of existence. During inflation, these quantum fluctuations in the inflaton field itself were not smoothed away. Instead, they were stretched from the microscopic quantum realm to macroscopic cosmic sizes. Regions where the inflaton field had a slightly higher energy density expanded ever so slowly, while regions with slightly lower density expanded a bit faster. These minute differences in the expansion rate translated into tiny variations in the density of the universe. After inflation ended, gravity went to work on these density imperfections. The slightly denser regions had a stronger gravitational pull, attracting more and more matter over billions of years. These became the seeds for the first stars, the great clusters of galaxies, and the vast cosmic web that structures our universe today. The entire majestic tapestry of the cosmos, with its billions of galaxies, originated from quantum jitters magnified to cosmic proportions by the inflationary expansion. This is a truly breathtaking connection. The largest structures we can observe were born from the smallest fluctuations allowed by the laws of physics. The pattern of hot and cold spots we see in the cosmic microwave background is a direct snapshot of these quantum seeds, a fossilized imprint of the universe's quantum origin. Inflation, therefore, is more than just a solution to a few cosmological puzzles. It is the hidden mechanism that transformed a random quantum fluctuation into an ordered, structured, and life-friendly universe. While the cosmic narratives of inflation and quantum branching paint a picture of unseen realms, one of the most direct and compelling pieces of evidence for a hidden layer of reality is something that exerts a powerful gravitational pull on everything we see, yet remains completely invisible. This brings us to our ninth theory, the profound mystery of dark matter. Imagine looking at a giant spiral galaxy like our own Milky Way, a vast pinwheel of stars, gas, and dust. You would naturally expect that stars closer to the galactic center, where most of the visible mass is concentrated, should orbit at tremendous speeds. Stars farther out in the sprawling spiral arms, feeling a weaker gravitational tug, should move much more slowly, just as Pluto orbits the Sun far more sluggishly than Mercury. But when astronomers like Vera Rubin measured the velocities of stars across galaxies in the 1970s, they found something that defied this basic logic. The stars out in the remote spiral arms were not moving slowly at all. They were orbiting at roughly the same high speed as the stars near the center. It was as if the entire galaxy, from its bright core to its faintest edges, was embedded within an enormous, massive sphere of something invisible. This something provides the extra gravitational glue needed to keep these swiftly moving outer stars from being flung off into intergalactic space. The only explanation is that there is far more mass in the galaxy than we can account for with luminous matter alone. This unseen mass, which does not emit, absorb, or reflect light, is what we call dark matter. The evidence for this hidden component doesn't stop at spinning galaxies. Another powerful line of proof comes from a dramatic effect predicted by Einstein's theory of general relativity, gravitational lensing. Massive objects warp the fabric of spacetime, causing light rays to bend as they pass by, much like a lens focuses light. When astronomers observe massive clusters of galaxies, they often see distorted, stretched, and magnified images of galaxies that lie far behind the cluster. The amount of bending is directly related to the total mass within the cluster. Astonishingly, the mass required to create these dramatic cosmic lenses is many times greater than the mass of all the visible stars and gas in the cluster combined. It's as if we're looking at a mountain peak and realizing that the vast bulk of the mountain is hidden beneath the surface with only the tip showing. This gravitational lensing provides a map of the dark matter, revealing its distribution in enormous halos that envelop galaxy clusters and form the invisible scaffolding upon which the visible universe is built. So what exactly is this mysterious substance that makes up about 27% of the cosmos? We know it interacts gravitationally, but it seems to be completely transparent to light and does not interact with normal matter through the electromagnetic force. Leading theories suggest it is composed of some new, exotic type of particle that has yet to be discovered. The primary candidate for decades has been a class of particles known as WIMP, or weakly interacting massive particles. As the name implies, these hypothetical particles would have a significant mass, perhaps dozens or hundreds of times the mass of a proton, and they would interact with normal matter only through the weak nuclear force and gravity. This extreme shyness is precisely what makes them so difficult to detect. The beauty of the WIMP hypothesis lies in what physicists call the WIMP miracle. Calculations from the early universe suggest that if a stable particle with a mass and interaction strength in the WIMP range were created in the Big Bang, its leftover abundance today would naturally account for the observed density of dark matter. It's a tantalizing convergence of particle physics and cosmology that has driven a multi-decade global hunt. This hunt takes place in some of the most extreme environments on and off Earth. To have any hope of detecting a WIMP, scientists must shield their experiments from the constant barrage of cosmic rays and background radiation that would overwhelm a potential dark matter signal. This has led to the construction of incredibly sensitive detectors placed deep underground in abandoned mines or beneath mountains. These labs use miles of rock as a natural shield. The detectors themselves are marvels of engineering, often consisting of vats of ultra-pure liquid xenon or germanium crystals, chilled to extremely low temperatures. The idea is to wait patiently for the once-in-a-lifetime event where a WIMP from the vast dark matter halo of our galaxy might, by sheer chance, collide with the nucleus of an atom in the detector, producing a tiny flash of light or a minute amount of heat that sophisticated sensors could, in theory, pick up. While there have been a few tantalizing hints over the years, a definitive, reproducible detection of WIMP has remained elusive. Given this challenge, other candidates have gained traction. A particularly compelling alternative is the action. Unlike the heavy WIMP, the action is theorized to be an incredibly light particle, billions of times lighter than an electron. It was originally proposed to solve a completely different puzzle in particle physics concerning the strong nuclear force. Actions would be produced in vast numbers in the early universe, and if they have a specific, very small mass, could collectively make up the dark matter. While individually wispy, their sheer abundance would add up to a dominant gravitational presence. The strategy for detecting actions is entirely different from the WIMP hunt. Instead of looking for nuclear recoils, experiments use powerful magnetic fields to try and convert actions into detectable microwave photons. It's a delicate needle in a haystack search, but one that is becoming increasingly sophisticated. The ongoing failure to find WIMP has led the physics community to broaden the search, considering other possibilities like sterile neutrinos or even macroscopic objects like primordial black holes formed in the first instance after the Big Bang. The true nature of dark matter remains one of the greatest unsolved problems in science, a silent testament to the fact that most of the universe's material content is made of something fundamentally different from the atoms that constitute you, me, and every star we can see. But if dark matter represents a hidden layer of mass weaving the universe together, our 10th theory reveals an even more enigmatic force pulling it apart. This is the mystery of dark energy, a discovery so shocking it upended our most fundamental assumptions about the cosmos's future. For much of the 20th century, scientists debated the ultimate fate of the universe. Would the collective gravity of all matter eventually halt the expansion from the Big Bang, causing the cosmos to collapse back in a big crunch? Or would the expansion simply continue forever, slowly coasting to a halt as galaxies drifted further and further apart? The answer, uncovered in the late 1990s, was neither. The universe's expansion isn't slowing down at all, it's speeding up. Galaxies are flying away from each other at an ever-increasing rate, as if some invisible repulsive force is stretching the very fabric of space itself. This revelation was made by two independent teams of astronomers who are meticulously studying a special class of stellar explosions known as Type 1a supernova. These cosmic detonations are invaluable because they are standard candles. They all explode with roughly the same intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance with remarkable precision. At the same time, by analyzing the redshift of their light, they can determine how fast the universe was expanding when the star blew up. When the teams compared supernova in extremely distant galaxies, meaning they exploded billions of years ago, to those in nearer, more recent galaxies, they made a staggering finding. The distant supernova were brighter than expected, indicating that the expansion of the universe was slower in the past than it is today. The universe's expansion is accelerating, a discovery that earned the researchers the Nobel Prize in Physics in 2011. This was akin to throwing a ball into the air and watching it not only fail to fall back down but shoot away from you faster and faster into the sky. Something was overpowering the relentless pull of gravity on a cosmic scale. So what is this mysterious something? the leading and simplest explanation is that dark energy is a property of space itself. Empty space, according to quantum field theory, is not nothing. It seethes with virtual particles that flicker in and out of existence. This vacuum energy exerts a negative pressure, and according to Einstein's theory of general relativity, such a pressure can produce a repulsive gravitational effect. Einstein himself had introduced a term into his equations called the cosmological constant to achieve a static universe, which he later called his greatest blunder when the expansion of the universe was discovered. Ironically, his blunder may turn out to be his greatest insight. If the cosmological constant is the answer, then dark energy has a constant, unchanging density as the universe expands. As new space is created, more dark energy appears to fill it, leading to a runaway acceleration. This scenario points toward a rather cold and lonely ultimate fate for the cosmos, often called the Big Freeze or heat death, where the acceleration becomes so extreme that distant galaxies are pushed beyond our observational horizon, and the universe becomes an ever-expanding, dark and empty void. However, the cosmological constant is not the only possibility. Another compelling idea is that dark energy is not constant but dynamic. This theory introduces a concept called quintessence, named after the fifth element of ancient philosophy. Quintessence would be a new type of energy field that permeates space, but unlike the cosmological constant, its strength could change over time. It could vary from place to place, and its repulsive force could either weaken or strengthen as the universe evolves. This opens up other potential futures. If quintessence weakens, the acceleration could slow or even reverse, perhaps leading to that long-theorized Big Crunch. If it strengthens, it could lead to a truly apocalyptic endgame known as the Big Rip, where the repulsive force becomes so powerful that it tears apart galaxies, then solar systems, then planets, and finally even atoms and nuclei themselves, shredding the very fabric of spacetime. The nature of dark energy is therefore not just an academic curiosity. It holds the key to the ultimate destiny of everything that exists. A third, more radical possibility is that dark energy isn't an energy at all. Instead, it could be a sign that our understanding of gravity, encapsulated by Einstein's theory of general relativity, is incomplete, especially on the very largest scales. Just as Newton's law of gravity needed an update to describe the extreme conditions near massive objects, Einstein's theory might need to be modified to account for the behavior of the universe as a whole. Perhaps gravity behaves differently over distances of billions of light years, weakening in a way that mimics the effects of a repulsive force. This would be a profound paradigm shift, suggesting that we need a new theory of gravity to truly comprehend the cosmos's hidden layers. Determining which of these explanations is correct, a cosmological constant, a dynamic quintessence field, or modified gravity, is one of the most pressing challenges in modern cosmology. Experiments like the Dark Energy Survey and the Future Euclid Space Telescope are creating detailed maps of the universe's expansion history and the growth of large-scale structure, searching for tiny clues that could distinguish between these competing ideas. Dark energy, constituting about 68% of the total energy budget of the universe, is the dominant component of reality, yet it remains the most mysterious. It is a hidden layer that not only shapes the cosmos but actively scripts its final chapter. After contemplating a cosmos hurled toward an ever-accelerating, lonely future by dark energy, we arrive at a theory that offers a dramatically different and far more hopeful vision of eternity. This is the cyclic model, a concept that proposes our universe has no true beginning and will have no final end. Instead, it is engaged in an endless, cosmic dance of death and rebirth, a perpetual cycle of fiery expansion and graceful contraction. This stands in stark contrast to the standard Big Bang narrative, which paints a linear story with a single, definitive starting point and an ultimate cold demise. The cyclic model suggests that our entire cosmic history, from the first flash of the Big Bang to the farthest future we can project, is merely one chapter in an infinite volume saga, a single layer in an endless series of universal epochs. One of the most compelling versions of this idea is the conformal cyclic cosmology proposed by the renowned physicist Roger Penrose. This is a particularly elegant and mind-bending framework because it doesn't rely on a big crunch where the universe collapses back on itself. Instead, it posits that our universe will continue expanding forever, but in a very specific way. As eons pass, all matter will eventually decay or be consumed by black holes. Those black holes will then slowly evaporate away due to Hawking radiation, until the universe contains nothing but a sparse sea of low-energy photons. At this point in the far, far future, the universe becomes effectively empty and featureless. With no particles of mass to define a scale, the concepts of space and time lose their meaning. Penrose proposes that this vast, cold, empty state is mathematically equivalent to the hot, dense, and equally featureless singularity from which our own Big Bang emerged. In this view, the remote future of one universe becomes the high-energy beginning of the next. The end is the beginning, and a new cycle of creation is triggered, not by a collapse, but by a conceptual transformation of the cosmos itself. Penrose even suggests there might be observable evidence for this in the cosmic microwave background, in the form of faint, concentric circles that could be the gravitational wave echoes of colossal black hole collisions from the previous eon. A different, equally fascinating approach to a cyclic universe builds directly upon the brain cosmology we explored earlier. This is the ekpyrotic cyclic model, which envisions the cosmic cycle as a periodic collision between our three-dimensional brain and a parallel brain floating in the higher dimensional bulk. In this scenario, the Big Bang is not a unique event but the recurring aftermath of a titanic impact. The cycle begins with the two brains drawn together by a force across the extra dimension, moving toward each other. When they collide, the immense kinetic energy is converted into the heat and radiation that ignites the hot Big Bang phase within our brain. Our universe then expands and cools, forming galaxies and stars and eventually being pulled apart by dark energy. But instead of leading to an eternal freeze, the dark energy plays a crucial role in setting the stage for the next cycle. It drives the brains apart and over an almost unimaginable timescale, dilutes the universe to near emptiness, effectively erasing any remnants of the previous cycle. Then, the attractive force between the brains takes over again, pulling them together for another collision and another Big Bang. This model creates a rhythm of cosmic renewal, where each cycle is born from the ashes of the last, with the brains acting like colossal cymbals clashing together at intervals spanning trillions of years. The most classic version of a cyclic universe, however, is the idea of the Big Bounce. This concept suggests that the expansion of our universe will eventually be halted and reversed by the collective gravity of all matter and energy. Galaxies would begin rushing back toward each other, the cosmic microwave background would heat up, and the universe would contract, getting hotter and denser. Instead of collapsing into an infinitely dense point, a singularity where our laws of physics break down, theorists propose that quantum gravitational effects, which become dominant at such extreme densities, would create a powerful repulsive force. This quantum pressure would act like a cosmic trampoline, causing the universe to bounce at a minimum size and begin expanding again in a new Big Bang. The universe would pulse, breathing in and out, with each cycle potentially lasting hundreds of billions of years. What's remarkable is that such a process could naturally explain the smoothness and flatness we observe without needing a period of inflation. The endless cycles of expansion and contraction would act like a cosmic iron, smoothing out any irregularities over countless iterations. Our universe isn't fine-tuned. It's simply very, very old and has been through this process an incalculable number of times. The appeal of the cyclic model in all its forms is profound. It offers a vision of a universe that is eternally resilient, a phoenix forever rising from its own ashes. It replaces the potentially bleak narrative of a one-time creation followed by an eternal fade with a story of perpetual renewal, suggesting that endings are always followed by new beginnings on the grandest scale imaginable. This endless cycle of cosmic rebirth presents a profound question. Why, in all these possible universes, is ours so hospitable to life? The laws of physics appear to be fine-tuned with an almost unbelievable precision. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, galaxies and stars would never have coalesced. The same delicate balance applies to the strong nuclear force, the mass of the electron, and the energy density of empty space. The odds of all these constants lining up perfectly by random chance seem astronomically small. This puzzle leads us directly to our 12th theory, a principle that sits at the crossroads of science and philosophy, the anthropic principle. In its simplest form, the anthropic principle is a statement of selective observation. It suggests that we must be cautious in the conclusions we draw about the universe because our very presence as observers imposes a bias. We can only find ourselves in a universe that has the right conditions to allow for our existence. This is known as the weak anthropic principle. It doesn't say the universe was designed for life. It simply acknowledges that we are here, so the universe we observe must be one of the ones capable of producing us. It's a self-evident truth, almost a tautology. Imagine a group of fish marveling at how perfectly water is suited to their biology. It's wet, it allows them to swim, it contains oxygen. They might conclude that water was designed specifically for fish, but the more rational explanation is that fish evolved to thrive in the environment that was already there. In the same way, we shouldn't be surprised that the universe is compatible with us. We are a product of its specific laws. The weak anthropic principle becomes a powerful explanatory tool when we combine it with the idea of a multiverse. If there are an infinite number of universes, each with randomly different physical constants, then it is no longer a staggering coincidence that we find ourselves in a life-friendly one. In the vast cosmic lottery, there will be countless universes where gravity is too strong or the weak force is too weak, rendering them sterile and lifeless. But there will also be a tiny, fortunate fraction where all the numbers line up just right. We, of course, can only exist in that rare, habitable subset. The fine-tuning isn't evidence of design. It's a consequence of our limited perspective, a selection effect on a cosmic scale. We are winners of a lottery, but we only become aware of our win because our existence is the prize. However, a much stronger and more controversial version of this idea exists, the strong anthropic principle. This version moves beyond mere observation and makes a bold claim about necessity. It proposes that the universe must have properties that allow life to develop at some stage in its history. The word "must" is crucial here. Proponents of the strong interpretation argue that the constants of nature are not randomly set. They are constrained by the requirement that they must lead to conscious observers. This can lead in some extraordinary directions. One interpretation suggests that the universe requires conscious observers to bring it into being, an idea that echoes certain philosophical idealism. Another, even more speculative line of thought is the participatory anthropic principle, proposed by physicist John Archibald Wheeler, which suggests that observers are necessary to give the universe definite form, that the act of observation itself is intertwined with the reality we perceive. The distinction between the weak and strong versions is critical. The weak anthropic principle is generally accepted as a logical and useful guideline in cosmology. It helps us avoid unscientific amazement at our own existence. The strong anthropic principle, on the other hand, is often criticized for venturing into the realm of untestable metaphysics. Critics argue that it attempts to explain the universe by invoking the very phenomenon conscious life. that we are trying to explain, potentially halting further scientific inquiry. Why is the universe fine-tuned? Because it must be. This can feel like a circular argument, yet for some, the strong principle remains a compelling way to grapple with the seemingly teleological or purpose-driven appearance of our cosmic home. It forces us to confront the possibility that life and consciousness are not accidental byproducts of the cosmos, but may be fundamental to its very nature. Whether viewed as a straightforward logical filter or a deep statement about cosmic necessity, the anthropic principle remains an essential lens through which we interpret our surprisingly hospitable place in the grand scheme of things. While string theory proposes extra dimensions as the path to quantum gravity, a radically different approach argues the solution lies not in adding new layers to reality, but in reimagining the very nature of space and time at the smallest possible scales. This is loop quantum gravity, a formidable and elegant competitor that seeks to describe the fabric of the cosmos without resorting to the existence of strings or hidden dimensions. Its core premise is one of breathtaking simplicity and profound implication. Space-time is not a smooth, continuous backdrop, as Einstein's general relativity assumes. Instead, it is granular, it is pixelated. Just as matter is composed of atoms and energy comes in discrete packets called quanta, loop quantum gravity posits that space itself is made of tiny, indivisible units. Imagine you have a beautifully smooth piece of fabric. To the naked eye, it appears perfectly continuous, but if you could look with a powerful enough microscope, you would see that the fabric is actually woven from individual threads. Loop quantum gravity suggests that the fabric of space-time is exactly like that. The smooth, continuous geometry we experience is an illusion that emerges from a vast network of intersecting loops, infinitesimal threads of gravitational field, woven together into a dynamic web. These loops are the fundamental building blocks, the atoms of space. In this framework, volume and area are not continuous quantities that can be divided infinitely. They come in discrete, tiny packets with a smallest possible unit of volume and a smallest possible unit of area, determined by the Planck scale. This is an incredibly small scale, about 10 to the negative 35 meters, far beyond our current ability to probe directly. At this level, the concept of here and there breaks down, replaced by a shimmering quantum network of relationships. This leads to a dramatic re-envisioning of the universe's origin. In the standard Big Bang model, if we rewind the cosmic film, all matter and energy are compressed into an infinitely dense and hot point, a singularity where the laws of physics as we know them cease to have any meaning. Singularities are generally seen as a sign that a theory is incomplete, a mathematical breakdown pointing to a deeper truth. Loop quantum gravity provides a powerful escape from this cosmic cul-de-sac. Because space is quantized, it cannot be compressed to an infinitely small point. Think of it like trying to compress a sponge. You can squeeze it, but eventually you reach a point where the solid structure of the sponge itself resists further compression. In the same way as the early universe collapsed under its own gravity in a previous cosmic cycle, the quantum nature of space would have created an immense repulsive force. Instead of crashing into a meaningless singularity, the universe would have reached a minimum possible size and then bounced back, beginning the expansion phase we observe as our Big Bang. This concept, known as the Big Bounce, transforms the Big Bang from a one-time creation event into a phase transition in an endless cosmic cycle. Our universe, in this view, may be the latest in an infinite series of universes, each born from the death of the one before it. It's a vision of cosmic resilience, a universe that breathes in and out over trillions of years. The appeal of loop quantum gravity lies in its directness. It takes the two pillars of modern physics, quantum mechanics and general relativity, and seeks to weave them together by quantizing the geometry of space-time itself, without requiring any additional, unobserved ingredients. While it remains a highly complex and developing theory, it offers a compelling and philosophically satisfying alternative to the hidden dimensions of string theory, suggesting that the deepest layer of reality might be a tapestry of finite, woven threads rather than a symphony of vibrating strings. But if the granular fabric of space-time in loop quantum gravity feels tangible, our next theory propels us into a realm of pure abstraction, proposing that the ultimate hidden layer of reality isn't a physical substance or a force, but something far more fundamental: mathematics itself. This is the mathematical universe hypothesis, championed by cosmologist Max Tegmark, and it stands as one of the most extreme and profound ideas in all of theoretical physics. It begins with a simple but powerful observation that has puzzled scientists and philosophers for centuries: the unreasonable effectiveness of mathematics in the natural sciences. Why is it that the universe, in all its chaotic complexity, appears to obey elegant mathematical rules? From the parabolic arc of a thrown ball to the precise orbits of planets described by Newton's equations, and further to the mind-bending predictions of general relativity and quantum mechanics that are confirmed to astonishing accuracy, mathematics provides a seemingly perfect language for describing the cosmos. The conventional view is that we invent mathematics as a tool to model a physical reality that exists independently of us. Tegmark turns this completely on its head. He proposes that we don't invent mathematical structures, we discover them, and the reason they describe our universe so perfectly is because our universe is a mathematical structure. Imagine a perfect circle. It exists as a concept in the abstract realm of mathematics, defined with absolute precision. You can draw a circle on a piece of paper, but it will always be an imperfect approximation, with bumps and irregularities at the microscopic level. The mathematical universe hypothesis suggests that our physical reality is like that perfect, abstract circle. The particles, forces, and even the space-time we inhabit are not just described by mathematical equations, they are the physical instantiation of those equations. In this view, the properties of an electron, its mass, its charge, its spin are not arbitrary values assigned by nature. They are necessary, logical properties of the specific mathematical structure that constitutes our universe. A conscious being, like you or me, is not a separate entity observing a mathematical universe from the outside. Instead, we are complex, self-aware substructures within the grand mathematical object, patterns of information that have evolved the capacity to perceive a tiny part of the larger structure they are embedded in. Tegmark organizes this radical idea into a compelling hierarchy, which he calls the 4 levels of the multiverse. The first level is the one we encountered earlier: the inflationary bubble universes, all sharing the same fundamental mathematical laws but with different initial conditions, like different solutions to the same set of equations. The second level introduces universes with different physical constants, emerging from the string theory landscape where the mathematical structure itself has different parameters. The third level is the quantum many-worlds branching, where all possible outcomes allowed by the wave function are realized. But it is the fourth and ultimate level that truly encapsulates the mathematical universe hypothesis in its purest form. This level contains not just all possible universes governed by the equations of physics as we know them, but all possible mathematical structures. This is a staggering expansion of the concept of reality. It includes universes with different numbers of spatial dimensions, universes governed by geometric rules we can't even conceive of, and universes so bizarre that our language has no words to describe them. If a mathematical structure is self-consistent, then, according to this hypothesis, it exists as a physical reality somewhere in the level 4 multiverse. To grasp the sheer scale of this idea, consider the set of all possible integers. It is an infinite set. Now, consider the set of all possible geometric shapes, then all possible equations, and then all possible axiomatic systems. The level 4 multiverse is the set of all these possibilities. Our universe is simply one specific mathematical structure within this infinite ensemble. This provides a dramatic answer to the question of why there is something rather than nothing. In the mathematical universe hypothesis, there is no nothing because the realm of mathematical existence is eternal and inevitable. It doesn't need a creator or a starting point, it just is. The challenge, of course, is that most of these mathematical structures would be utterly incomprehensible and uninhabitable. They might be chaotic, transient, or devoid of any stable patterns that could be interpreted as complexity or life. We find ourselves in one of the rare, ordered mathematical structures that is complex enough to allow for self-aware substructures to evolve. This connects back to the anthropic principle. Our existence as observers selects for a universe with mathematical laws that support our form of consciousness. The implications of this hypothesis are simultaneously elegant and deeply unsettling. It suggests that the quest for a final theory of everything is not the search for the ultimate particle or force, but the search for the specific mathematical structure that corresponds to our physical reality. Once we identify that structure, every property of our universe, from the value of the cosmological constant to the number of generations of quarks, would be a logical and necessary consequence with no free parameters left to adjust. It would represent a final, complete understanding of existence, yet it also implies a certain passive nature to reality. If the universe is a static mathematical object, then our experience of the flow of time, of cause and effect, is merely an emergent property within the structure, an illusion perceived by the self-aware patterns within it. We are not actors on a stage, we are intricate patterns woven into the timeless tapestry of mathematics. While this theory is currently untestable in any conventional sense, it forces a fundamental shift in perspective, challenging us to consider that the deepest layer of reality might not be physical at all, but a world of perfect, eternal, and breathtakingly beautiful mathematical truth. Moving from the abstract perfection of a mathematical cosmos, we now dive back into the tangible yet equally fantastic predictions of Einstein's own theory. General relativity gave us black holes, cosmic objects so dense that not even light can escape their grip. But the mathematics of this powerful theory is surprisingly balanced, and for every solution that describes a one-way street into oblivion, it offers a mirror image, a theoretical exit door. This brings us to the astonishing concepts of white holes and wormholes, tunnels and fountains in the fabric of space-time itself. First, consider the white hole. If you were to take the equations for a black hole and literally run the clock backwards, you would get a white hole. Instead of an event horizon from which nothing can escape, a white hole would possess an event horizon from which nothing can enter. It would be a region of space-time that violently ejects matter and energy while refusing to allow anything from the outside to cross its boundary. Think of a black hole as a cosmic drain, forever pulling everything in. A white hole, then, would be a cosmic fountain, perpetually spewing material out. While this is a perfectly valid mathematical solution, whether such objects actually exist in nature is a major open question. Some theorists have speculated that the Big Bang itself could be viewed as a primordial white hole, a singular eruption of all the matter and energy in the cosmos. Others have suggested that if a black hole ever fully evaporates through Hawking radiation, its final moments might involve a transformation into a white hole. However, white holes are considered highly unstable, if not outright impossible, according to the second law of thermodynamics, as they would represent a massive decrease in entropy, a reversal of the universal trend toward disorder. They remain a fascinating what-if at the edge of theoretical physics, but if white holes are a speculative in point, their conceptual cousin offers a far more dynamic possibility. This is the wormhole, often called an Einstein-Rosen bridge. Imagine space-time as a vast, flat sheet of paper. If you want to get from point A to point B on that sheet, you have to travel the entire distance across the surface. But what if you could fold the paper, bringing points A and B directly together, and then punch a hole through the resulting fold? That shortcut through the higher dimension is the essence of a wormhole. It's a tunnel, a shortcut through the fabric of space-time that could connect two distant points in our universe, or, even more incredibly, bridge the gap between two entirely separate universes in a multiverse. The possibility arises directly from Einstein's equations. In 1935, Albert Einstein and his colleague Nathan Rosen realized that the mathematical description of a black hole could be extended to form a bridge to another region of space-time. The standard picture involves a black hole singularity, a point of infinite density, but their solution suggested this singularity could be avoided, leading through a narrow throat to a corresponding white hole in another location or another universe entirely. This is the classical Einstein-Rosen bridge. There is, however, a monumental catch. These primordial wormholes, as predicted by the equations, would be incredibly unstable. The tunnel would likely collapse into a singularity faster than the speed of light, meaning even a single photon couldn't make the journey before the passage pinched shut. Using such a bridge for travel would be like trying to run through a hallway that is crumbling and sealing shut right behind you. This is where the concept of exotic matter enters the picture. To prop a wormhole open long enough for anything to traverse it, you would need a substance with a truly bizarre property: negative energy density, or equivalently negative pressure. Normal matter, which has positive energy density, always exerts an attractive gravitational force which would cause the wormhole throat to collapse instantly. Exotic matter, however, would generate a repulsive gravitational effect, pushing the walls of the tunnel apart and stabilizing it. While this sounds like pure fantasy, glimpses of such negative energy densities do appear in quantum physics, most famously in the Casimir effect. When two uncharged, perfectly smooth metal plates are placed extremely close together in a vacuum, they experience a slight attractive force. The reason is that the space between the plates restricts the kinds of quantum fluctuations that can occur, resulting in a lower energy density between the plates than in the surrounding space. This creates a tiny, measurable negative energy density. The problem is scale. The amount of exotic matter required to hold open a wormhole large enough for a spacecraft would be astronomical, perhaps equivalent to the mass energy of Jupiter or even a star, all with negative energy. Whether such quantities can exist without violating fundamental physical principles is a topic of intense debate. If such an engineering marvel were ever possible, the implications would redefine our place in the cosmos. A stable, traversable wormhole would be the ultimate interstellar shortcut, allowing for journeys across the galaxy that would take hours instead of millennia. But the consequences go even deeper, straight into the realm of time travel. According to general relativity, if one end of the wormhole were moved at a significant fraction of the speed of light relative to the other end, time dilation effects would cause time to pass at different rates for the two mouths. Let's say you have a wormhole created in 2024. You keep one end, mouth A, stationary on Earth. You put the other end, mouth B, on a spaceship and send it on a journey at near light speed for 10 years from the perspective of Earth. Due to time dilation, only, say, 1 year might pass for the crew and mouth B. When mouth B returns to Earth in the year 2034, it would only be 1 year older than when it left. This means anyone stepping into mouth B in 2034 would exit from mouth A not in 2034, but in 2025, emerging 9 years into their own past. This creates a closed time-like curve, a path through space-time that loops back on itself. The potential for paradoxes is immediate. What if you traveled back and prevented your own birth? This is the famous grandfather paradox. Physicists like Stephen Hawking proposed the chronology protection conjecture, which suggests that the laws of physics may inherently prevent such time travel through mechanisms we don't yet understand. perhaps through a buildup of quantum energy that destroys the wormhole the moment it becomes a time machine. While wormholes and white holes remain in the domain of theoretical exploration and science fiction, they push our understanding of gravity to its absolute limits, revealing a universe where the lines between space, time, and possibility are far more blurred than we ever imagined. Now, let's shift our focus from cosmic structures to a deeply personal and unsettling puzzle that strikes at the very heart of our own existence. This is the Boltzmann brain paradox, a thought experiment so bizarre it forces us to question whether our own consciousness is a reliable layer of reality or the ultimate cosmic fluke. The paradox emerges from a seemingly innocent corner of physics, the second law of thermodynamics. This law states that the universe, on the whole, tends toward a state of maximum disorder or entropy. Think of a hot cup of coffee cooling in a room. The heat disperses, moving from a state of concentrated order to a more uniform, disordered state. Over vast stretches of time, the universe itself is thought to be heading toward a final state known as heat death, a cold, dark, and utterly uniform soup of particles where nothing interesting ever happens again. But here's the twist. In a truly random system, even as entropy increases overall, there can be tiny, temporary fluctuations that create pockets of order. It's statistically improbable, but not impossible, for all the air molecules in a room to spontaneously rush into one corner for a split second. In an infinite or eternally expanding universe that exists for an unimaginably long time, the improbable becomes not just possible but inevitable. Given enough time, every possible configuration of matter, no matter how unlikely, will occur through random chance. This includes the spontaneous assembly of a fully formed, conscious human brain, complete with all its intricate neural connections and a complete set of false memories floating alone in the void. This hypothetical entity is what physicists call a Boltzmann brain, named after the 19th century physicist Ludwig Boltzmann, who pondered these ideas. The terrifying implication is this: if such a brain were to randomly fluctuate into existence, its experience would be indistinguishable from your own. It would wake up, so to speak, with the memory of having a childhood, of learning to walk, of watching this very video. It would possess a coherent, internally consistent reality, all fabricated in an instant by a random quantum accident. The universe it believes it inhabits, a universe with galaxies, a history, and laws of physics, would be nothing more than an elaborate hallucination. The paradox then asks a devastating question. In an eternal universe headed for maximum disorder, which scenario is more statistically probable? Is it more likely that an entire, orderly, 13.8 billion-year-old universe evolved precisely to produce you, a conscious being with a real past? Or is it vastly more likely that a single, disembodied brain with fake memories just popped into existence a moment ago? The mathematics of probability seem to suggest the latter. The spontaneous creation of one brain is astronomically more likely than the spontaneous creation of an entire universe full of stars, planets, and billions of other brains. Therefore, if our universe is eternal and random, the odds overwhelmingly suggest that you and I are not the products of a long, ordered cosmic evolution, but are instead these freakish, momentary glitches in a sea of chaos. This conclusion is so philosophically unacceptable to most physicists that it is used as a powerful argument against certain cosmological models. If a theory of the universe, like one featuring an eternal cosmological constant-driven expansion, inevitably leads to the prediction that Boltzmann brains will vastly outnumber ordinary brains, then that theory is considered deeply flawed or incomplete. It becomes a reductio ad absurdum, a way of showing that our current understanding must be missing a crucial piece. Perhaps the universe is not eternal in the way we think. Perhaps it will eventually cycle or reset before these bizarre fluctuations can dominate. Or perhaps the nature of consciousness itself is not what we assume, and a spontaneously created brain without a body or an external world could not truly be conscious. The Boltzmann brain paradox serves as a stark reminder that our search for the universe's hidden layers must ultimately include an inquiry into the nature of our own perception, forcing us to confront the unsettling possibility that the most fundamental layer of our reality might be our own, potentially unreliable mind. But what if we are approaching the entire dark matter puzzle from the wrong angle? What if the mysterious substance isn't missing at all, but rather our fundamental understanding of gravity itself is incomplete, at least under certain extreme conditions? This brings us to a bold and controversial alternative that directly challenges the dark matter paradigm: modified Newtonian dynamics, or MND. Instead of filling the cosmos with invisible particles, MND proposes a far more radical solution. It suggests that Isaac Newton's famous law of gravity, and by extension Einstein's more general theory, requires a slight but crucial modification when the gravitational force becomes exceptionally weak. The core insight of MND is that this threshold occurs precisely in the environments where dark matter's effects are most pronounced: the vast, sparse outer regions of galaxies. The theory was first proposed by physicist Mordechai Milgrom in the early 1980s, sparked by the very same galactic rotation curve problem that pointed to dark matter. Milgrom noticed something fascinating: the discrepancy between the predicted and observed speeds of stars in galaxies didn't appear when you looked at the absolute distance from the center. Instead, it kicked in when the acceleration experienced by those stars fell below a specific, very tiny value, about 100 billionth of the acceleration we feel from Earth's gravity. This critical acceleration threshold is astonishingly small, but it seems to be a universal key. Milgrom proposed a simple modification. When the gravitational acceleration drops below this threshold, Newton's inverse square law ceases to be entirely accurate. Instead of the force of gravity diminishing with the square of the distance, the decline becomes more gradual. This tiny tweak to the equations produces a dramatic effect. It provides just enough extra gravitational pull in the outskirts of galaxies to keep high-speed stars in their orbits, perfectly replicating the observed flat rotation curves without a single gram of dark matter. It's as if we've been trying to measure things with a ruler that shrinks slightly at very large scales. MND proposes a correction to the ruler itself, suggesting that gravity behaves differently in the relative quiet of deep space compared to the stronger gravitational fields of our solar system. The appeal of MND is its striking success and simplicity at a specific scale. For individual galaxies, especially isolated dwarf galaxies and those with low surface brightness, MND predictions often match the observed rotation curves with remarkable precision, sometimes even outperforming complex dark matter simulations that require careful tuning of a galaxy's dark matter halo. It appears to be a natural law that emerges directly from the visible mass of stars and gas, offering a clear, predictive formula that works for a wide variety of galactic structures. This has led its proponents to argue that MND is more than just a curious idea. It reveals a fundamental principle of nature that has been overlooked, a deeper layer to the law of gravity that only becomes apparent in the most gentle gravitational fields. However, for all its elegance in explaining galaxies, MND faces profound challenges when confronted with the full breadth of cosmological evidence. The first major hurdle is the behavior of galaxy clusters. These colossal gatherings of hundreds or even thousands of galaxies are enveloped in incredibly hot gas that emits X-rays. By measuring the temperature and distribution of this gas, astronomers can calculate the total mass needed to hold the cluster together. While MND does reduce the amount of missing mass in clusters compared to standard Newtonian gravity, it doesn't eliminate it entirely. There still appears to be a significant mass deficit, requiring some form of unseen matter even within the MND framework, though perhaps not as much as the dark matter model suggests. The most dramatic and often cited evidence against MND, however, comes from a spectacular cosmic collision known as the Bullet Cluster. This system consists of two galaxy clusters that have recently smashed right through each other. During such a collision, the individual stars in the galaxies, being so far apart, pass by each other mostly unaffected, like two swarms of bees interpenetrating. The hot gas clouds within each cluster, however, interact strongly through electromagnetic forces, much like two clouds of smoke, and they get slowed down and stuck in the middle of the collision. What astronomers observed was truly startling. By using gravitational lensing to map the total mass distribution, they found that the bulk of the mass, the source of the gravitational lensing effect, was not located with the visible galaxies, and it was not stuck with the gas in the center. Instead, the mass had clearly sailed right through the collision site, leading the visible galaxies. This is exactly what you would expect if the mass were made of dark matter particles that, like the stars, hardly interact with each other or with the gas. For Mund, this observation is exceptionally difficult to explain. If gravity is purely a modification of the laws based on the distribution of visible matter, then the gravitational lensing should be strongest where the visible matter is most concentrated with the galaxies and the central gas cloud. The fact that the gravity is clearly separated from the visible mass poses a severe problem, suggesting that there truly is a separate, collisionless component to the mass that can be pulled apart from the normal matter. Proponents of Mund have developed more complex relativistic versions of the theory, such as tensor vector scalar gravity, or TVS, which incorporate additional fields to try and account for these lensing observations, but these models often become cumbersome and lose the elegant simplicity that made Mund so attractive in the first place. The debate between dark matter and Mund is far from settled. It represents a fundamental fork in the road of theoretical physics. Is the universe filled with a vast, unseen ocean of exotic particles that dominate its mass? Or have we, for centuries, been slightly mistaken about how gravity works in the most extreme environments? Dark matter fits seamlessly into our standard model of cosmology, explaining everything from the cosmic microwave background to the large-scale structure of the universe. Mund, meanwhile, offers a compelling and predictive alternative for galactic dynamics without invoking new particles. The ongoing search for dark matter particles and continued observations of galactic and cluster dynamics will ultimately determine which of these hidden layers, an unseen substance or a modified force, is the true architecture of our cosmos. While the bizarre predictions of quantum mechanics can feel like abstract mathematical curiosities, some of the greatest minds in physics have sought a more intuitive picture, a way to visualize the hidden reality that lies beneath the quantum weirdness. One of the most profound and philosophically rich attempts came from physicist David Bohm, who proposed that our familiar world is just the surface expression of a far deeper, more interconnected level of existence. He called this framework the implicate order, and it presents a radical reinterpretation of what reality might actually be. Bohm was deeply troubled by the standard Copenhagen interpretation of quantum mechanics, which seemed to relegate reality to a probabilistic haze until an observer forced it to make a choice. He was particularly fascinated by quantum entanglement, the phenomenon Einstein famously called spooky action at a distance, where two particles remain mysteriously linked regardless of the space between them. For Bohm, this non-locality wasn't a spooky anomaly, it was a crucial clue. It suggested that the separation between objects we perceive is an illusion, and that at a fundamental level, the entire universe is an unbroken whole. To describe this, he introduced two complementary concepts, the explicate order and the implicate order. The explicate order is the world we experience every day. It's the unfolded, manifest reality where things have distinct locations, clear boundaries, and exist in a definite state. A chair is here, a table is there. You are separate from the screen you're watching. This is the world of classical physics, a world that appears to be built from separate parts interacting through local forces. Bohm argued that this explicate order is a secondary, derivative reality. It emerges from a far more primary and fundamental level, which he termed the implicate order. The word implicate comes from the Latin for enfolded. In the implicate order, everything in the universe is folded into everything else. The entire cosmos is intricately woven together in a state of dynamic, unbroken flow. Nothing is truly separate. The distinctions we see are merely temporary unfoldings from this deeper, enfolded background. To make this abstract idea more tangible, Bohm offered a beautiful analogy: a droplet of ink in a viscous fluid like glycerin. Imagine a cylinder with a closely fitting rod inside it. If you place a single drop of ink in the glycerin and then slowly turn the rod, the droplet will be drawn out into a fine, thread-like strand, eventually becoming so finely dispersed that it becomes invisible to the naked eye. The ink has become enfolded into the glycerin. Its order is now implicate. Now, if you reverse the rotation of the rod, the seemingly random distribution of ink will gradually coalesce, and the original droplet will magically reappear. The droplet has been unfolded back into the explicate order. In this analogy, the entire universe is like that glycerin, and every object we see, every atom, person, and galaxy is like a temporary, unfolded droplet. The underlying reality is the continuous, flowing medium in which all things are enfolded and from which they emerge. This connects powerfully to another analogy Bohm used: the hologram. In an ordinary hologram, every single fragment of the photographic plate contains information about the entire three-dimensional image. If you break a hologram into pieces, you don't get pieces of the object. You get smaller, slightly fuzzier versions of the whole object. Bohm suggested that the universe itself might operate on a similar principle. At the level of the implicate order, every region of space-time contains, in an enfolded state, the totality of the entire cosmos. The particle that appears here and the particle that appears a billion light-years away are not separate entities sending signals to each other. Instead, they are both unfoldments from the same deeper, holistic background. Their entanglement is no longer spooky. It's a natural consequence of their shared origin in the implicate order, where their connection is immediate and total. This perspective offers a stunningly elegant resolution to some of quantum mechanics' most enduring puzzles. Take wave-particle duality. In Bohm's view, a particle, like an electron, is always a real particle with a definite position. But it is guided by a new, non-local entity Bohm called the quantum potential, or the pilot wave, which originates from the implicate order. This quantum potential carries information about the entire experimental setup, and it guides the particle along a definite path that creates the statistical patterns we interpret as wave-like behavior. The particle doesn't spread out like a wave. It is a localized object being guided by a wave of information from the deeper, interconnected whole. The famous double-slit experiment, where a single electron seems to interfere with itself, is explained not by the electron being in two places at once, but by the quantum potential, informed by the presence of both slits guiding the electron to locations that build up an interference pattern over time. Bohm's implicate order is more than just a scientific theory. It's a comprehensive worldview that bridges physics and philosophy. It suggests that the fragmentation we experience, the sense of being separate individuals in a world of separate objects, is a feature of the explicate order, a useful but ultimately limited perspective. The true nature of reality is one of unbroken wholeness, a flowing, dynamic process where consciousness itself may not be a mere byproduct of the brain, but an active participant in the unfolding of reality from the implicate to the explicate. While Bohm's interpretation is not the mainstream view in physics, often criticized for its non-locality and the difficulty of testing it experimentally, it stands as a powerful testament to the human desire to find a coherent, intuitive, and deeply meaningful picture of the cosmos's hidden layers, one where connectivity, not separation, is the fundamental truth. But if the mathematical universe hypothesis presents a cosmos of cold, elegant equations, Our 19th theory re-injects a startling dose of warmth and agency back into the center of the cosmic story. This is the participatory anthropic principle, a profound and radical idea championed by the legendary physicist John Archibald Wheeler. He took the logical filter of the anthropic principle and turned it into an active, creative force, suggesting that the universe requires conscious observers not just to be noticed but to truly become real. In Wheeler's view, we are not passive inhabitants of a pre-existing reality. We are active participants in its ongoing creation, and consciousness itself may be the most fundamental hidden layer of all. Wheeler was deeply influenced by the bizarre paradoxes of quantum mechanics, particularly the notion that the act of observation seems to force a quantum system to choose a definite state. He saw this not as a mere laboratory curiosity, but as a profound clue about the nature of existence itself. He famously summarized his vision with the phrase "it from bit," proposing that every particle, every field, every force of nature, the entire it of the physical world ultimately derives its existence from the bits of information elicited by acts of observation. In this digital cosmology, the universe is fundamentally an information processing system, and questions posed by observers are what generate the answers that we perceive as tangible reality. To illustrate this mind-bending concept, Wheeler devised a series of brilliant thought experiments, the most famous of which is the cosmic scale delayed choice experiment. Imagine a single photon, a particle of light, traveling for billions of years from a distant quasar. On its journey, it is gravitationally lensed by an intervening galaxy, meaning its path is bent, and it can now approach Earth from two slightly different directions. We can set up an apparatus with two telescopes, each aimed to capture light from one of these paths. If we simply record which telescope the photon arrives in, it behaves like a particle having taken one specific route. But if we place a device that forces the light from the two paths to recombine and interfere with itself, the photon suddenly behaves like a wave, implying it must have traveled both paths simultaneously. The staggering implication of Wheeler's experiment is this: we make this decision whether to measure the particle's path or its wave nature after the photon has already been traveling for billions of years. Our choice in the present seems to retroactively determine what the photon did in the distant past. Did it travel as a particle on a single path or as a wave on both paths? The answer depends on how we choose to measure it now. The past, in a very real sense, is not fixed until it is observed in the present. Wheeler extrapolated this idea to its ultimate conclusion. He proposed that the entire universe is, in effect, one vast delayed choice experiment. The universe began with the Big Bang, a quantum event of immense potentiality, a haze of probability. For billions of years, it evolved in a state of unresolved potential, a superposition of countless possible histories. It was only with the eventual emergence of conscious life, of observers like us, equipped with the capacity to look back and measure, that this fog of possibilities collapsed into a single, concrete timeline. Our act of observing the cosmic microwave background, of studying the light from ancient galaxies, and of tracing the history of the cosmos is what forces the universe to have a specific past. We are participants in a grand cosmic feedback loop where the universe gives rise to observers, and those observers, through the very act of observation, give definite reality to the universe that created them. It's a closed circuit of Genesis, a self-excited circuit where existence calls itself into being. This view elevates consciousness from a mere byproduct of complex brain chemistry to a fundamental, irreducible component of reality. It suggests that the physical world is not the primary reality, but rather a manifestation of a deeper, information-theoretic or conscious realm. The participatory anthropic principle doesn't just say the universe is fine-tuned for life, it says the universe is brought into full being by life. This idea resonates with certain strands of philosophical idealism, which posit that reality is fundamentally mental. While it remains a highly speculative and controversial interpretation, far from the scientific mainstream, it challenges the traditional subject-object dichotomy in a profound way. It forces us to consider that the search for the universe's hidden layers might ultimately lead us not outward to distant dimensions, but inward to the very nature of our own awareness. In Wheeler's participatory universe, we are not just stardust contemplating the stars. We are the mechanism by which the stars acquire their history and their meaning, partners in a cosmic dance of creation that stretches from the first moment to the last. Now, let's journey to a theory that turns the cosmos inside out, suggesting that the greatest cosmic prison might also be the ultimate cosmic womb. This is the hypothesis that our entire universe exists within a black hole residing in a much larger parent universe. At first glance, this seems like a fantastical inversion of reality, but it emerges from a striking mathematical similarity that has captivated cosmologists. Consider the fundamental description of a black hole's core, a point of infinite density and temperature, a singularity where the laws of physics as we know them break down. Now rewind our cosmic history to the first moment of the Big Bang. What do we find? A point of infinite density and temperature, a singularity. The equations that describe these two seemingly different events are eerily analogous. This has led some physicists to propose they are not just similar, they might be the same phenomenon viewed from two different perspectives. From the outside, a black hole is a region of space-time from which nothing can escape. But what happens on the inside? According to general relativity, once you cross the event horizon, space and time swap their roles. The radial direction toward the singularity becomes a time-like direction, a one-way path to the future. In this twisted geometry, the singularity isn't a place you can point to in space. It is a moment in time that everything inside the black hole is inevitably racing toward. This sounds remarkably like our own experience of the universe. We are all moving forward in time toward a future state. In the black hole universe model, the Big Bang singularity wasn't the beginning of everything. It was the moment of our formation, the moment our space-time geometry was born from the collapse of matter in a parent cosmos. The relentless expansion of our universe, then, is simply the continued evolution of space-time away from that singular moment as experienced from within. This idea finds further support when we look at the numbers. The observable universe has a finite size and contains a finite amount of mass and energy. If you calculate the Schwarzschild radius, the size of the event horizon, for a mass equivalent to everything in our observable universe, the result is astonishingly close to the actual estimated radius of the observable universe itself. It's a compelling coincidence that suggests our cosmic home could be comfortably contained within its own event horizon, invisible and inaccessible to any outside observer. From this vantage point, the galaxies rushing away from us aren't just expanding into space, they are falling inward through time toward their ultimate fate, much like matter falling toward the central singularity of a black hole. This framework provides a breathtakingly elegant explanation for the Big Bang itself. In the parent universe, the formation of our universe would have begun with a colossal stellar collapse, a supermassive star giving birth to a black hole. But from our perspective inside that black hole, that event was the white hole explosion we call the Big Bang. A white hole, as we discussed, is the theoretical time reversal of a black hole, a singularity that ejects matter and energy rather than absorbing it. So, while an observer in the parent universe would see a black hole forming and matter vanishing behind an event horizon, we, on the inside, experienced that same event as a glorious, fiery beginning, a fountain of space-time and matter erupting into existence. The Big Bang becomes a cosmic echo of a gravitational collapse in a higher dimensional reality. The implications of this are as vast as they are mind-bending. If our universe was born from a black hole in a parent universe, then it's a logical next step to propose that every black hole formed within our own cosmos could itself contain a brand new universe. Every time a massive star collapses or two black holes merge, the formation of a new event horizon might simultaneously create a new spacetime continuum within, complete with its own laws of physics and its own cosmic history. This creates a fractal multiverse, an infinite nesting doll of realities. Our entire cosmos, with its hundreds of billions of galaxies, could be just one tiny bubble in a frothing foam of universes, each existing within the black holes of a higher-level universe, which itself may reside within a black hole of an even greater cosmos. This vision offers a form of cosmic immortality. The death of a star in our universe is not an end, it is a genesis. The information that falls into a black hole, which seems lost to our reality, may not be destroyed but instead serve as the initial conditions for an entirely new cosmic story, forever hidden from our view but teeming with its own potential for life and complexity. It is a theory that beautifully intertwines the beginning and the end, suggesting that creation and destruction are two sides of the same cosmic coin. While many theories of quantum gravity search for hidden layers in extra dimensions or vibrating strings, another powerful approach suggests the ultimate building blocks of reality might be far more straightforward, constructed from the simplest geometric shapes imaginable. This is the theory of causal dynamical triangulation, a framework that dares to ask a revolutionary question. What if the smooth, continuous fabric of space-time is an illusion, emerging from a microscopic landscape that is fundamentally chunky and pixelated? The name itself reveals the core of the idea. Triangulation refers to the use of tiny geometric building blocks, specifically triangular pyramids or simplexes, which serve as the indivisible atoms of space. Dynamical indicates that these blocks are not static. They can be rearranged, defining a history, a dynamics for the cosmos. And most importantly, causal imposes a crucial rule on how these blocks can connect to one another. A rule that ensures cause always precedes effect, preserving the logical flow of time that we hold so dear. Imagine you are tasked with building a complex curved surface, but you are only allowed to use small, flat triangular tiles. If the tiles are large and few, the surface will be blocky and faceted, like a crude video game model. But if you use an enormous number of incredibly tiny tiles, the surface can approximate a smooth, flowing curve with arbitrary precision. Causal dynamical triangulation applies this exact same logic to the entire universe. It proposes that space-time is not a smooth manifold, but is instead a vast patchwork of these elementary geometric tiles. Each tile is a tiny chunk of space-time, a Planck-scale building block with a simple, fixed geometry. The magic and the profound hidden layer lies in how these tiles are allowed to fit together. The theory doesn't just throw the tiles into a random pile. It imposes a strict rule of causality, meaning the connections between tiles must respect the natural ordering of time. A tile representing a moment now can only connect to tiles representing moments in the future in a consistent way, preventing paradoxical situations where an effect could precede its cause. To see how a universe emerges from this, physicists use a powerful technique akin to a cosmic dice roll. They start with a colossal number of these space-time tiles and let the rules of quantum mechanics dictate how they can be assembled. This process is like running a massive computer simulation, where every possible way of gluing the tiles together, every possible history for the universe, is considered, but each history is weighted by a probability derived from the theory's equations. It's a statistical process, a sum over all possible geometric configurations that obey the causal rule. From this quantum froth of countless random triangulations, something truly remarkable happens. When the simulations are run, the theory doesn't produce a chaotic jumble of dimensions. Instead, it spontaneously predicts the emergence of a universe that is large-scale, smooth, and has exactly 4 dimensions, 3 of space and 1 of time. This is a breathtaking result. The 4-dimensional continuum of our everyday experience is not an assumption put into the theory. It is an output, a natural consequence of the simple rules governing the microscopic, triangular building blocks. The smooth fabric of reality arises from the collective behavior of an unimaginably vast number of discrete, quantum geometric pieces, much like the smooth appearance of a material emerges from the chaotic jostling of its individual atoms. This success in generating a four-dimensional world is what makes causal dynamical triangulation so compelling. It suggests that the dimensionality of our universe might not be a fundamental, predetermined fact, but rather a phase of matter, an emergent property that arises under the right conditions, much like ice crystallizes into a specific structure when water freezes. The theory provides a concrete, computable model for how the cosmos could transition from a chaotic, quantum geometric foam at the smallest scales to the orderly, classical stage upon which galaxies and life can evolve. It represents a profound shift in perspective, revealing a hidden layer of geometric simplicity that underlies the complex continuum we inhabit. A universe built not from mysterious substances, but from the pure, elegant logic of geometry and causality. Now we reach a conjecture so elegant it seems to weave the very fabric of space-time from the threads of quantum connection. This is the ER equals EPR proposal, an idea that dares to unite two of Einstein's most enduring legacies, which he himself thought were entirely separate. On one side, we have the ER, standing for Einstein-Rosen bridges, the wormholes we just explored, those hypothetical tunnels through the geometry of space-time. On the other side, we have EPR, named for the famous Einstein, Podolsky, and Rosen paper that first highlighted the bizarre, spooky phenomenon of quantum entanglement. For decades, these two concepts lived in different worlds. Wormholes were a dramatic prediction of general relativity, the theory of the very large, while entanglement was a baffling feature of quantum mechanics, the theory of the very small. The ER equals EPR conjecture, championed by physicists Juan Maldacena and Leonard Susskind, makes a breathtakingly simple yet radical claim. These are not two different things. They are, in fact, two different descriptions of the same fundamental reality. An Einstein-Rosen bridge and a pair of entangled particles are one and the same. To grasp the power of this idea, let's first recall the spookiness of entanglement. When two particles become entangled, they form a single, unified quantum system. Measuring one particle, say, finding its spin pointing up instantly determines the state of the other, even if it's on the opposite side of the galaxy. This instantaneous connection seems to violate the speed of light limit imposed by relativity, a paradox that deeply troubled Einstein. Now imagine a different kind of connection, a microscopic wormhole, a Planck-scale tunnel linking the locations of these two particles. If information could travel through this tunnel, it wouldn't have to break the light speed barrier. It would simply take a shortcut through the extra-dimensional bulk, creating the illusion of spooky action at a distance. In this geometric picture, entanglement isn't a mysterious, non-local force. It's a manifestation of a physical bridge, a tiny, subatomic thread stitching the universe together. The particles aren't communicating faster than light. They are, in a very literal sense, touching each other through a hidden dimension. This perspective transforms our understanding of what happens when we try to pull entangled particles apart. In the standard quantum view, the entanglement remains a fragile, invisible link. In the ER equals EPR view, as you separate the particles, the microscopic wormhole connecting them is stretched. It becomes longer and longer, like pulling on a piece of incredibly elastic taffy. This provides a stunningly intuitive geometric explanation for why you can't use entanglement to send a faster-than-light message. Any attempt to manipulate one particle to send a signal would require sending a physical object or a ray of light through the wormhole. But because the wormhole is stretched and incredibly narrow, it would be effectively non-traversable. The signal would take so long to navigate the elongated tunnel that it would never beat a beam of light traveling directly through normal space. the spookiness is tamed by geometry. The implications of this conjecture extend far beyond explaining a single quantum phenomenon. It offers a potential roadmap to the holy grail of physics, a theory of quantum gravity. The greatest conflict between general relativity and quantum mechanics is the black hole information paradox. Quantum mechanics insists that information can never be destroyed, but general relativity suggests that anything falling into a black hole is lost forever behind the event horizon. ER equals EPR provides a breathtakingly elegant escape clause. Imagine two entangled particles. One falls into the black hole while its partner remains outside. According to the conjecture, these two particles are connected by a microscopic wormhole. This means the particle inside the black hole and the particle outside are not truly separate. They are two ends of the same cosmic string. The information about the infalling particle isn't trapped inside the black hole. It is encoded in the entanglement between the internal and external particles. When the black hole eventually evaporates through Hawking radiation, the entanglement is transferred to the radiation itself, preserving the information in a complex, scrambled form. The wormhole in this picture is the mechanism that ensures information is never lost, seamlessly bridging the gap between the smooth geometry of relativity and the informational rules of quantum mechanics. This idea finds its most concrete realization in the context of the holographic principle we discussed earlier. In the famous AD/S/CFT correspondence, a gravitational theory in an anti-de Sitter space is perfectly equivalent to a quantum field theory without gravity on its boundary. ER equals EPR gives this abstract duality a powerful geometric interpretation. The entanglement between degrees of freedom on the boundary, a purely quantum phenomenon, is what creates the geometric fabric of the interior bulk. In simpler terms, the space-time within the universe, complete with its wormholes, is literally woven from the quantum entanglement on its boundary. It's a concept that turns reality inside out. The three-dimensional world we experience, with its forces and matter, emerges from a vast web of quantum connections on a distant two-dimensional surface. The ER equals EPR conjecture suggests that quantum entanglement is the fundamental resource from which the geometry of space-time itself is built. Every connection, every bond, every thread of reality might ultimately be a manifestation of this profound quantum relationship, revealing a hidden geometric layer that underpins the entire cosmos. From the mind-bending possibility that entanglement weaves the fabric of space-time, we now turn to a concept that acts as a cosmic guardian, a fundamental rule that may lock away one of the most tantalizing hidden layers forever. This is Stephen Hawking's chronology protection conjecture, a bold proposal that the laws of physics have a built-in safety mechanism to prevent time travel to the past. While wormholes and other structures might mathematically allow for journeys backward in time, Hawking argued that nature abhors a paradox so profoundly that it will always find a way to slam the door shut. It's a theory not about a hidden layer of reality, but a powerful statement about why certain layers specifically, those involving closed time-like curves, must remain permanently inaccessible to us. Hawking's reasoning began with a simple but powerful observation. If time travel to the past were possible, then where are all the tourists from the future? The universe isn't overrun with visitors from tomorrow, which suggests that time travel, at least on a macroscopic scale, isn't happening, but he wanted a deeper physical reason. He suspected that the very act of trying to create a time machine would trigger a catastrophic feedback loop in the quantum fields that permeate the vacuum of space. Think of empty space not as true nothingness, but as a seething sea of virtual particles. These particle-antiparticle pairs constantly pop into existence, borrow energy from the vacuum for an infinitesimally short time, and then annihilate each other, returning the energy. This is a well-understood quantum phenomenon. Now, imagine you have a wormhole that you've engineered into a time machine, perhaps by moving one mouth at relativistic speeds. As particles begin to loop through this time travel circuit, they can interact with their own past selves. A single photon, for instance, could travel back in time and interact with the version of itself that is just about to enter the wormhole. In the bizarre world of quantum mechanics, this interaction can amplify the photon's energy. Hawking and others showed that this amplification wouldn't just happen once, it would happen over and over again in a runaway feedback loop. The energy of the particle would circulate endlessly, building upon itself with each pass, rapidly escalating to infinity. This isn't a gradual heating, it's an instantaneous, catastrophic explosion of energy. The vacuum fluctuations around the entrance to the time machine would become infinitely energetic, creating a wall of radiation so intense that it would destroy the wormhole itself before any information or matter could complete a journey to the past. It would be like trying to force sound through a microphone and speaker that are too close together. You get a screeching feedback squeal that forces you to turn down the volume. In the case of a time machine, the squeal is an infinitely powerful burst of quantum energy that turns down the time machine to zero by vaporizing it. The conjecture suggests that this isn't a mere engineering challenge, it's a fundamental law of physics. Any attempt to create a closed time-like curve, a path through space-time that loops back on itself, will inevitably trigger these vacuum fluctuations, producing a radiation field of infinite energy that destroys the possibility. Nature, in essence, has a paradox police that arrives on the scene with overwhelming force the moment a causal loop is about to be established. The beauty of the chronology protection conjecture is that it doesn't just apply to wormholes. It's a general principle that would protect the past from any kind of manipulation, whether through rotating cosmic strings, Tipler cylinders, or any other hypothetical device. It preserves the arrow of time and the essential sanity of cause and effect, ensuring that history remains fixed and unchangeable. Without such a principle, the logical foundation of reality would crumble. The famous grandfather paradox, where you travel back in time and prevent your own grandfather from meeting your grandmother, becomes more than a philosophical puzzle. It represents a logical inconsistency that physics seems wired to avoid at all costs. Hawking's conjecture provides a physical mechanism for that avoidance. While it remains a conjecture, an educated guess that hasn't been rigorously proven as a theorem, it carries the weight of Hawking's profound insight into the relationship between gravity, quantum theory, and the nature of time. It suggests that the linear, irreversible flow of time we experience may be more than just a perceptual artifact. It could be a deeply ingrained, protected feature of the cosmos, a rule so fundamental that the universe would rather tear itself apart than allow it to be broken. But as we've explored the vast mathematical possibilities of string theory, from extra dimensions to the multiverse, a critical question has emerged from within the physics community itself. Does this incredible theoretical freedom come at a cost? If string theory can describe 10 to the power of 500 different possible universes, is it a theory of everything or a theory of anything? This internal struggle has given rise to a powerful conceptual framework for distinguishing genuine physical potential from mathematical mirages, a framework known as the landscape and the swampland. It's a meta-theory, a set of principles that might govern which of the countless hidden layers are truly physically possible. The concept of the landscape is both the great promise and the profound challenge of string theory. We encountered it earlier with the Level 2 multiverse. It's the staggering conclusion that the equations of string theory don't yield a single, unique solution. Instead, they permit a colossal number of stable configurations for the extra dimensions, a number so vast it dwarfs the count of atoms in our observable universe. Each point in this landscape corresponds to a specific way those tiny dimensions are curled up, and each unique fold dictates the laws of physics for that particular universe. One fold might give rise to a universe with 4 fundamental forces and 3 generations of quarks like our own. Another might produce a cosmos with 5 forces and utterly different particles. The landscape is the set of all these mathematically self-consistent possibilities. For some, this is a virtue. It provides a potential explanation for the fine-tuning of our universe. We simply inhabit one of the rare, life-friendly corners of this vast cosmic archipelago. The landscape suggests that the quest for a single, unique theory of everything might be misguided. The fundamental theory is one of vast potentiality, and our local physics is just one accidental outcome. However, this immense freedom has led to a significant criticism. If a theory can accommodate almost any observed outcome, how can it make testable predictions? How do we know which point in the landscape, if any, corresponds to our reality? This is where the concept of the swampland enters the debate. A group of physicists began to ask a more refined question. Just because a low-energy physical theory like the Standard Model coupled with gravity is mathematically consistent on its own, does that mean it can be successfully embedded into a full theory of quantum gravity like string theory? The Swampland program proposes that the answer is no. They argue that there is a swampland of effective field theories that, while seemingly consistent, cannot be completed into a consistent theory of quantum gravity. They are, in effect, stranded in the theoretical wetlands, disconnected from the solid ground of true quantum gravity, which they call the landscape. The goal of the Swampland program is to identify the criteria, the conjectures that separate the landscape from the swampland. These are not yet proven theorems, but rather powerful hypotheses based on deep insights from black hole physics and string theory constructions. One of the most discussed is the swampland distance conjecture. It suggests that as you move a long distance in the field space of a theory, for example, by changing the value of a scalar field like the dilaton, which is related to the strength of forces, an infinite tower of new, incredibly light particles appears. Their emergence effectively destabilizes the original description, preventing you from reaching a point in the landscape where, say, a fundamental constant is truly zero or infinite. This conjecture implies that our universe's apparent stability is precarious. If we could somehow dial the value of a constant too far, the entire particle zoo would change dramatically, preventing the physics we know from existing in those extreme regions. Another key conjecture is the swampland de Sitter conjecture, which has direct implications for one of the biggest discoveries in modern cosmology, dark energy. This conjecture casts doubt on the existence of long-lived, stable universes with a positive cosmological constant. That is, universes like ours that are undergoing accelerated expansion due to dark energy. It suggests that such configurations might be in the swampland, unable to be properly realized in a full theory of quantum gravity. If this conjecture holds, it would mean that our current understanding of dark energy as a constant vacuum energy is fundamentally flawed. Instead, dark energy might be a dynamic field like quintessence that is slowly evolving and will eventually decay. This isn't just an academic exercise, it's a bold, falsifiable prediction that could guide future cosmological observations. If experiments continue to confirm that the dark energy density is truly constant, it could pose a serious challenge to string theory as currently understood, or force a revision of the swampland criteria. The tension between the landscape and the swampland represents a fascinating and healthy meta-debate within theoretical physics. It's a self-imposed quality control mechanism. The landscape liberally allows for a multiverse of possibilities, while the swampland conjectures act as stringent filters, attempting to isolate which of those possibilities are truly physically plausible. This isn't about proving string theory right or wrong in one go. It's about refining our understanding of the necessary conditions for any theory of quantum gravity. By studying the boundaries of what is allowed, physicists hope to uncover deeper principles that must be obeyed by the ultimate theory, principles that might eventually lead us to unique, testable predictions about our own universe. It's a profound effort to impose order on the dizzying possibilities of the hidden layers, arguing that even in a vast multiverse, not everything goes. Among the many cosmic riddles we've explored, few strike at the very core of physics, quite like the black hole information paradox. This isn't just a curiosity, it's a fundamental conflict between our two most successful theories of reality, and its resolution may require us to rewrite the rulebook of the universe. The problem centers on a sacred principle of quantum mechanics. Information can never be truly destroyed. Think of it this way. If you were to burn a book, the paper and ink would turn to smoke and ash. To all appearances, the information, the story, the words is gone. But a hypothetical superintelligence with perfect knowledge of the laws of physics could, in principle, collect every particle of smoke, trace every photon of light, and reverse engineer the exact state of the book before it was burned. The information was scrambled, but it was never lost. Quantum mechanics insists this is always true. The universe, at its heart, is a meticulous record keeper. Now bring a black hole into the picture. According to Einstein's general relativity, if you throw that same book into a black hole, it crosses the event horizon and is irretrievably lost. The book and all its information is crushed into the singularity at the center. For decades, this was seen as a one-way trip to oblivion, but then Stephen Hawking made a revolutionary discovery. He realized that black holes aren't completely black. Due to quantum effects near the event horizon, they slowly emit a faint glow of radiation, now known as Hawking radiation. This radiation carries away energy, causing the black hole to lose mass and, over astronomical timescales, completely evaporate. Here lies the catastrophic paradox. The Hawking radiation is random, purely thermal, and contains no information about what fell into the black hole. It's like the heat coming off a hot stove. It tells you the temperature, but nothing about what fuel is burning. So, when the black hole finally vanishes, what happens to the information from the book? Quantum mechanics says it must be preserved somewhere. But general relativity, combined with Hawking's calculation, suggests it has been permanently erased from the universe. This is the information paradox. Two foundational pillars of physics make directly contradictory predictions. One of the most elegant proposed solutions brings us back to the holographic principle. You'll recall this idea suggests that all the information about a three-dimensional volume can be encoded on its two-dimensional boundary. For a black hole, this boundary is the event horizon. The proposal is that when an object falls in, it doesn't actually pass through unchanged. Instead, its information is immediately smeared out and stored as a kind of ultra-dense pixelation on the surface of the event horizon. The three-dimensional object is transformed into a two-dimensional hologram. Then, as the black hole emits Hawking radiation, this process is not perfectly smooth. Tiny imperfections, quantum fluctuations in how the information is encoded on the horizon, can be imprinted onto the escaping radiation. In this view, the information doesn't vanish with the black hole. It is slowly and meticulously leaked back out, bit by bit, in a heavily scrambled code. To an outside observer, it would look like random noise, but in principle, the information is preserved. The paradox is solved by recognizing that the interior of the black hole is a projection, and the true information content of the universe remains safely on the surface. However, this holographic solution comes with a startling and violent implication: the firewall paradox. If information is encoded on the event horizon, what does that mean for someone falling in? According to Einstein's principle of equivalence, crossing the event horizon of a large black hole should be an uneventful experience, at least initially. There should be no dramatic local sign that you've passed the point of no return. But if the horizon is a busy information processing surface, violently scrambling and encoding data, this smooth passage becomes impossible. The quantum fields at the horizon would have to be in a highly excited state to perform this encoding, creating a searing wall of energy, a firewall, that would instantly incinerate any astronaut falling into the black hole. So we are left with a brutal choice. Either information is lost, violating quantum mechanics, or the event horizon is a lethal firewall, violating general relativity. It seems we must sacrifice one cherished principle to save the other. A different class of solutions challenges Hawking's original assumption that the radiation is purely thermal. This is the idea of quantum entanglement. Before the black hole forms, the quantum fields of empty space are entangled in a complex web. When Hawking radiation is produced, it arises in pairs of particles. One falls into the black hole, and its entangled partner escapes. Hawking argued that the entanglement between these pairs gets transferred to the entanglement between the radiation and the black hole's interior, but in a way that eventually leads to a problem called monogamy of entanglement. The alternative is that the escaping particles become entangled with the radiation that left earlier, preserving the overall quantum information without needing a firewall. The information is subtly carried out by the intricate entanglement patterns within the Hawking radiation itself. This aligns with the ER equals EPR idea, where entanglement and wormholes are two sides of the same coin, suggesting the information has a geometric pathway to escape. The black hole information paradox is more than an academic debate. It is a powerful beacon, illuminating the precise point where our current understanding of gravity and quantum mechanics fractures. Its eventual resolution will not just solve a puzzle about black holes. It will force us to peer into a hidden layer of reality where space, time, and information are woven together in a way we are only beginning to imagine. Returning to the elegant idea of supersymmetry, we encounter its most significant practical hurdle, the profound silence of our detectors. If this beautiful symmetry is a true law of nature, then where are all the superpartners? The answer to this question lies in a crucial concept known as supersymmetry breaking. In a perfect, unbroken state of supersymmetry, every known particle would have a superpartner with exactly the same mass. The electron and the selectron would be mass twins. The photon and the photino would be indistinguishable in weight. If this were the case, we would have discovered these particles decades ago. They would have shown up in every high-energy experiment, as common as the particles we know. The fact that we haven't seen them is the clearest indication that supersymmetry, if it exists, is not perfect in our current low-energy universe. It is a broken symmetry. Think of it like a magnet. At a very high temperature, a magnet is symmetric. It has no preferred north-south orientation, but as it cools, it undergoes a phase transition. It spontaneously chooses a direction to magnetize, and in doing so, the perfect symmetry is broken. Supersymmetry is thought to have undergone a similar process in the early universe. At the tremendously high energies present just after the Big Bang, supersymmetry may have been perfect. Particles and sparticles were mass equals, but as the universe expanded and cooled, it settled into a lower energy state where the symmetry is hidden. The superpartners acquired very large masses, making them incredibly heavy and difficult to produce, while the standard model particles remained relatively light. This breaking is the reason the selectron isn't sitting next to the electron in our periodic tables. It was catapulted into a realm of mass far beyond what our current colliders can easily reach. The how of this breaking is a major focus of theoretical research, and several compelling models have been proposed. One of the most prominent is gravity-mediated supersymmetry breaking. In this elegant scenario, the force that transmits the breaking across the cosmos is none other than gravity itself, but in a very specific way. The idea is that supersymmetry breaks in a hidden sector of the universe, a realm of particles that interacts with our familiar world only through gravity. The messenger of this breaking is a hypothetical particle called the gravitino, the superpartner of the graviton, which is the hypothetical particle that would carry the force of gravity. Because gravity is so incredibly weak, the effect of the breaking is diluted by the time it reaches our sector, resulting in superpartners that are heavy, but not impossibly so, with masses in the range of a few hundred to a few thousand times the mass of a proton. This is a range that the Large Hadron Collider was specifically designed to probe. Another fascinating possibility is gauge-mediated supersymmetry breaking. Here, the messengers are not gravitational, but are instead the known gauge forces of the Standard Model, like the strong and electroweak interactions. In this model, a set of new messenger particles feels the supersymmetry breaking directly, and then transmits it to the particles of the Standard Model through their known interactions. Because these forces are much stronger than gravity, the transmission is more direct, leading to a very specific prediction. The lightest supersymmetric particle would be the gravitino, and it would be extremely light. This model also predicts that the superpartners of the Standard Model particles would have a very characteristic mass pattern, a signature that physicists could search for in the debris of particle collisions. The discovery of a particular pattern of supersymmetry breaking would therefore not just confirm the theory, but would also tell us something profound about how the hidden sectors of the universe communicate with our own. So, why have we not found them yet? The simplest answer is that nature has chosen a path where the superpartners are heavier than the energy thresholds we have so far achieved. The initial optimism that supersymmetry would appear at the energies accessible to the LHC was based on the hope that the new particles would be light enough to solve the hierarchy problem neatly. The fact that they haven't been seen has pushed the possible mass scale higher, into a range that is more challenging for the collider to produce. Producing these heavy particles requires collisions of unprecedented energy, and even then, they would be rare events, lost in a sea of trillions of Standard Model interactions. It's a needle in a haystack search of cosmic proportions. Furthermore, the way these particles decay would leave subtle signatures, an imbalance in the momentum of the collision products, or specific combinations of jets and missing energy, that require incredibly sophisticated detectors and complex data analysis to identify. The ongoing search is far from over. The non-discovery so far is itself valuable data, ruling out vast swaths of the simplest supersymmetry models and forcing theorists to be more creative. It has led to the exploration of scenarios like stealth supersymmetry or R-parity violation, where the lightest supersymmetric particle is not stable and dark matter, or where the superpartners decay in ways that leave even subtler traces in the detector. Each new model presents a new challenge for experimentalists and a new puzzle to solve. The hunt continues not just at the LHC, but also in dedicated experiments searching for the effects of these particles in rare particle decays or in the precise measurement of the magnetic moment of the muon, where a tantalizing discrepancy with the Standard Model prediction has persisted for years, a possible hint of supersymmetric effects. Finding supersymmetry would be one of the most monumental discoveries in the history of science, revealing a hidden layer of particles that would fundamentally rewrite our understanding of the universe's most basic building blocks. But what if the very stage of space and time we've been discussing wasn't always there? What if, in the universe's first fleeting moments, the concepts of here and there were utterly meaningless? This brings us to a theory that reimagines the birth of geometry itself, the quantum gravity hypothesis. Picture the newborn universe not as a tiny, dense point in a pre-existing void, but as a seething, chaotic network of pure potential. In this vision, reality began not as a smooth continuum, but as an abstract graph, a vast, tangled web where every single node was directly connected to every other node. There was no distance, no separation, because everything was adjacent to everything else. This primordial state was a perfect democracy of connection, a universe of infinite dimensions in a sense, because you could step from any one point to any other without crossing an interval. It was a blazingly hot, disordered soup of links, a realm where the very idea of geometry had yet to be invented. Then something remarkable happened. As the universe expanded and cooled, it underwent a cosmic phase transition, much like water freezing into ice. This was not a transition of matter, but of space-time itself. The hyper-connected graph, unstable in its chaotic unity, began to crystallize. Connections between distant points became energetically costly and began to snap, while local connections stabilized and strengthened. Think of it like a million people in a giant room, all shouting to be heard at once. As the energy dies down, they naturally form smaller, local groups, conversing only with their immediate neighbors. The all-to-all connectivity gives way to a structured, orderly network. In the case of the universe, this process froze the graph into the familiar, low-dimensional structure we inhabit today. The three dimensions of space and one of time that we experience are not fundamental. They are emergent properties, a pattern that condensed out of a more basic, abstract network of relationships. The vast distances between galaxies and the orderly progression of cause and effect are the frozen-in relics of this ancient phase transition. This hypothesis offers a stunningly elegant perspective on one of cosmology's deepest puzzles. Why does our universe have exactly three spatial dimensions? In the quantum gravity framework, the number of dimensions isn't written into the fundamental laws. It is the result of a random fluctuation that got locked in during the freezing process, much like the specific six-sided symmetry of a snowflake is not preordained but emerges from the physics of crystallization. Other universes in a multiverse could have frozen into two dimensions or four or more. Our cosmic home has three not because it's special, but because that was the stable configuration that formed as the graph cooled. This turns our understanding of reality inside out. We are not living in a pre-formed container. We are living within a pattern, a specific vibrational mode of a deeper, hidden layer of connectivity. The smooth fabric of space-time is an illusion that emerges from the collective behavior of countless discrete quantum links. A reality woven from a web of relationships where the distance between 2 points is ultimately defined not by an empty void, but by the number of connections you must traverse to get from one to the other. After exploring theories that suggest space-time is granular or emerges from quantum graphs, we now turn to an idea that weaves together two of cosmology's greatest puzzles into a single, elegant geometric explanation. This is the theory of dark dimensions, a framework that proposes a stunning possibility. Dark matter and dark energy are not real substances at all. Instead, they are cosmic mirages, phantom effects created by the hidden geometry of our universe's position within a higher dimensional reality. Imagine you are a character living on the surface of a vast, expanding balloon. You can only perceive the two dimensions of the balloon's skin. As the balloon inflates, you would observe all other points on the surface moving away from you at an accelerating rate. You might invent a mysterious, dark energy force to explain this expansion, but the real cause would be the balloon's growth into a third dimension that you cannot see. The dark dimensions theory applies this same logic to our entire cosmos, suggesting we are that two-dimensional character, but on a far grander scale. This theory builds upon the foundation of brane cosmology, where our universe is a three-dimensional membrane or brain floating within a higher dimensional bulk. The novel twist here is the nature of the extra dimension. Unlike the tiny, curled-up dimensions of string theory, this model proposes at least one extra dimension that is surprisingly large, perhaps even infinite in size. Our brain is not static, it is dynamically evolving, slowly expanding or stretching into this large extra dimension. It is this gradual, geometric evolution that is proposed to manifest as the twin mysteries of dark matter and dark energy. The gravitational force, being the one force not confined to our brain, can leak out into this extra dimension. This leakage has two profound consequences that perfectly mimic the effects of the two dark components. First, as gravity spreads out into the larger volume of the bulk, its strength within our brain becomes diluted. From our perspective, this weakening of gravity in the vast outskirts of galaxies looks exactly as if there is extra, unseen mass providing additional gravitational pull, the precise effect we attribute to dark matter. The gravitational field of a galaxy isn't being generated by invisible particles. It's being shared with or lost to the hidden dimension, creating the illusion of missing mass. Second, the theory offers a geometric origin for dark energy. The relentless acceleration of the universe's expansion could be a direct result of the brain's own motion through the bulk. As our brain expands into the extra dimension, its dynamics could naturally produce an effective negative pressure, driving the observed acceleration. It's not that empty space has an inherent energy. It's that the very fabric of our reality is stretching into a hidden direction, and that motion, when translated into our three-dimensional physics, looks like a repulsive force. This provides a potential unification that has eluded cosmologists for decades. Instead of two separate, unexplained entities, one an invisible matter and the other a mysterious energy, both phenomena are seen as different facets of a single cause, the interaction between our brain and a large extra dimension. The appeal is immense as it replaces two enigmatic things with one elegant geometric principle, a hidden layer of reality that is purely about the shape and motion of space itself. However, like all compelling theories, the dark dimensions model faces significant challenges. The primary hurdle is formulating a precise mathematical framework that can exactly replicate the incredibly detailed observational data we have, from the precise rotation curves of individual galaxies to the large-scale structure of the cosmic web and the specific expansion history of the universe measured by supernova. A generic leakage of gravity might produce effects that resemble dark matter and dark energy in a broad sense, but matching the fine details requires a very specific and stable configuration. Furthermore, if gravity is indeed leaking into a large extra dimension, this could have subtle but detectable effects on gravitational waves or in high-precision experiments measuring the force of gravity at short distances. So far, no such definitive signal has been found. The theory remains a highly speculative but fascinating frontier, a testament to the creativity of cosmologists striving to find a simpler, more fundamental architecture behind the universe's greatest mysteries. It challenges us to consider that the answers we seek may not lie in discovering new particles, but in finally perceiving the full, hidden geometry of the stage upon which the cosmic drama unfolds. While the search for WIMP and actions continues, a radically different solution to the dark matter puzzle has been gaining traction, one that requires no new fundamental particles at all. Instead, it proposes that the invisible mass weaving galaxies together is made of objects we already know exist, but from a different, far more ancient origin story. This is the primordial black hole hypothesis, a compelling idea that suggests a hidden layer of the cosmos is populated not by exotic particles, but by countless ancient black holes, relics from the universe's explosive first moments. These wouldn't be the stellar mass black holes we're familiar with, born from the violent deaths of massive stars. Those form far too late in cosmic history and in insufficient numbers to account for all the dark matter. Primordial black holes, or PBHS, are something else entirely. They are theorized to have formed not from stellar collapse, but from the extreme conditions in the very early universe, less than a second after the Big Bang. During this period, space was not perfectly smooth. Thanks to quantum fluctuations, there were tiny, random variations in density. Some regions were ever so slightly denser than others. In most of the universe, radiation pressure from the intensely hot plasma smoothed out these wrinkles. But in regions where the density fluctuation was particularly pronounced, gravity could win out. If a patch of space was dense enough, its own gravitational pull could overcome the outward pressure, causing it to collapse directly into a black hole. The mass of these primordial black holes would be determined by the size of the region that collapsed, which was governed by the cosmic horizon at that instant the maximum distance light could have traveled since the Big Bang. This means PBHS could theoretically span a vast range of masses, from microscopic ones as light as an asteroid to supermassive behemoths thousands of times heavier than our Sun. This wide mass range is both a feature and a challenge of the theory. Over the decades, astronomers have used a variety of clever methods to search for these hidden objects, and in doing so, have ruled out many possible mass ranges. One of the most powerful techniques is gravitational microlensing. The principle is straightforward. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, bending the starlight and causing the star to temporarily brighten. By monitoring millions of stars in nearby galaxies like the Large and Small Magellanic Clouds, projects like the MACHO and OGLE surveys have placed stringent limits. They've shown that black holes in the mass range of a typical star, from about 1/10 to 100 times the mass of our Sun, cannot make up more than a small fraction of the dark matter. If they did, we would see far more of these microlensing events than we actually do. Another critical constraint comes from the cosmic microwave background. If a large number of primordial black holes were evaporating in the early universe via Hawking radiation, they would have injected significant energy into the surrounding gas, altering the precise pattern of the CMB that we observe today. This has largely ruled out very low mass PBHS, those lighter than about an asteroid, as a dominant component of dark matter, as they would have evaporated away completely by now. Perhaps the most exciting recent constraints come from the field of gravitational wave astronomy. The LIGO and Virgo observatories have detected the ripples in spacetime from merging black holes. Some of these black holes fall into a mass range tens of solar masses. That is difficult to explain through standard stellar evolution. This has led to a resurgence of interest in the idea that these could be primordial black holes. However, if a vast population of such objects was zipping around the galaxy as dark matter, their frequent encounters and mergers would produce many more gravitational wave signals than LIGO has seen. The current data suggests that while some of the detected black holes could be primordial, they likely don't constitute the entirety of the dark matter. So, where does that leave us? The viable window for PBHS to be all the dark matter has been narrowed considerably. The most promising remaining mass range is now thought to be in what's called the asteroid mass window, from about the mass of a small asteroid to that of our Moon. In this range, these black holes would be small, numerous, and incredibly difficult to detect directly. They would neither evaporate quickly nor cause frequent, observable microlensing or merger events. Another intriguing, though more speculative, possibility is that a smaller population of much larger primordial black holes, perhaps thousands of solar masses, could exist and act as seeds for the supermassive black holes we find at the centers of galaxies today. The primordial black hole hypothesis remains a powerful and elegant alternative to particle-based dark matter. It challenges us to consider that the solution to one of cosmology's greatest mysteries might not lie in the quantum realm, but in the gravitational fossils of the universe's own tumultuous birth, a hidden layer of reality built from the densest objects the laws of physics allow. And so we arrive at the final and perhaps most profound question of all. After this grand tour of hidden dimensions, parallel worlds, holographic projections, and cosmic symmetries, we are left standing before the ultimate goal of physics, the quest for a theory of everything. This is not just another layer to add to the list. It is the dream of a framework so complete and elegant that it would weave every one of these disparate threads into a single, unified tapestry. It is the search for the one set of equations, the foundational principle, from which all the laws of nature, from the frantic dance of quantum particles to the majestic curvature of spacetime, would inevitably flow. The ambition is breathtaking: to hold the universe's entire operating manual in one hand. This drive for unification is the golden thread running through the entire history of science. We saw it when Isaac Newton realized the same force that pulls an apple to the ground governs the moon's orbit around the Earth. We saw it when James Clerk Maxwell united electricity, magnetism, and light into a single theory of electromagnetism. And we saw it most spectacularly with Albert Einstein, who spent the later decades of his life in a lonely, determined struggle to merge his theory of gravity, general relativity, with the emerging rules of quantum mechanics. He believed with a quiet conviction that the universe was fundamentally simple and rational at its core, and that its apparent complexity was merely a veil hiding a deeper, harmonious order. His failure to find that final theory did not diminish the quest. It passed the torch to a new generation of physicists armed with even more powerful tools. Today, the leading candidate for this ultimate theory is string theory. Its promise is immense. It replaces the confusing zoo of point-like particles with a single, fundamental entity, tiny, vibrating loops of energy. The different vibrational patterns of these strings, like the notes on a violin string, would correspond to all the different particles we see. A specific vibration gives you an electron, a different one gives you a quark, another gives you the photon. In this symphony of strings, gravity is no longer an outsider. The graviton, the hypothetical carrier of the gravitational force, emerges naturally as just another vibrational mode. The theory mathematically requires extra dimensions of space, providing a potential home for all the hidden layers we've explored. For a time, it seemed like the perfect, beautiful answer. But the path to a theory of everything is littered with formidable challenges. String theory, for all its elegance, has yet to make a single testable prediction that can be verified in a laboratory. Its landscape of possible solutions is so vast that it risks becoming a theory of anything, and therefore a theory of nothing. Competing approaches like loop quantum gravity offer a different path, quantizing space itself, but so far struggling to incorporate the other forces of nature. The sheer difficulty of the problem has led some of the brightest minds to a startling and humbling possibility. What if a single, final theory is a mirage? What if reality is not a pyramid with one fundamental law at the bottom, but more like an infinite onion, with every layer you peel back revealing yet another, equally fundamental layer beneath? This perspective suggests that the concept of fundamental might be a human construct, a desire for a neat and tidy ending to the cosmic story. Nature, however, may be inherently layered. The rules that govern biology are consistent with the rules of chemistry, which are based on the rules of atomic physics, which are built upon quantum mechanics. But is the biology any less real than the quantum fields? Each level of complexity might have its own emergent laws and principles that, while consistent with the layer below, cannot be easily reduced to it. Trying to explain the beauty of a symphony solely in terms of the physics of vibrating strings, while technically possible, misses the entire point of the music. Perhaps the universe is the same. The search for a theory of everything might successfully reveal the next layer down a world of strings or spin networks, but that layer itself might be built upon something even more mysterious in an endless chain of explanation. This brings us to the philosophical heart of the journey. Is the true value of this quest the destination, or is it the journey itself? Even if a theory of everything is never found, or if it is found to be an unattainable ideal, the pursuit has been one of humanity's most glorious achievements. It has pushed our intellect to its absolute limits, forced us to invent new mathematics, and given us profound insights into the nature of reality, from the cosmic microwave background to the Higgs boson. The search forces us to confront the deepest questions about existence, consciousness, and our place in the cosmos. It is a story of curiosity, perseverance, and the audacious belief that the human mind can comprehend the universe's deepest secrets. Whether we ultimately find a single equation etched on a cosmic tablet or discover an endless labyrinth of layers, the act of searching expands what it means to be human. We are the universe becoming aware of itself, peering into its own hidden depths, and in that act of looking, we participate in the greatest story ever told. And so we arrive at the end of our extraordinary journey, having ventured through 30 of the most mind-expanding ideas about the nature of reality. From the infinite bubbles of the inflationary multiverse to the quantum branching of the many worlds, from the possibility that we live in a cosmic hologram to the chance our entire existence is an advanced simulation, we have stretched the very limits of imagination. We have confronted the chilling silence of dark matter and the phantom force of dark energy, danced with the elegant symmetry of supersymmetry, and even peered into the granular fabric of space-time itself. While it is crucial to remember that many of these theories remain in the realm of profound speculation, untested by experiment, they represent something far more significant than mere fantasy. They are the absolute frontier of human curiosity, the product of our species' relentless and courageous drive to push beyond the visible, to ask what if. On the grandest possible scale, the common thread weaving through this vast tapestry of ideas is a humbling and exhilarating realization. The universe is almost certainly far stranger, more complex, and more deeply layered than our everyday senses could ever suggest. The reality we perceive directly, the solid ground beneath our feet, the familiar cycle of day and night, is merely the surface of an ocean whose depths we are only beginning to fathom. Each theory, in its own way, attempts to pull back a corner of the veil, revealing hidden architectures of extra dimensions, parallel histories, and fundamental connections that defy our classical intuition. This is not a sign of failure in our understanding, but a testament to its progress. We are like explorers who have mapped the coastline of a vast continent, now realizing that the interior holds mountains and valleys, forests and deserts of a scale and wonder we had never before dared to dream. This journey does not end here, it simply continues with you. The most fascinating question now is not which theory is correct, that is for future experiments and generations to decide, but which of these visions of reality resonates most deeply with your own sense of wonder. Does the idea of an infinite multiverse, where every possible version of you is living out every possible life, fill you with a sense of cosmic freedom or an existential dread? Does the holographic principle, suggesting our richly three-dimensional world is a projection from a distant two-dimensional surface, strike you as elegant or unsettling? Perhaps the thought that consciousness itself might be a fundamental participant in creation, as the participatory anthropic principle suggests, feels like an empowering homecoming. We want to know what you think. Share your thoughts in the comments below. Which of these 30 theories do you find the most compelling, the most beautiful, or the most utterly terrifying? If this exploration into the hidden layers of the cosmos has ignited your curiosity, then you are exactly where you belong. This channel is dedicated to diving deep into the universe's greatest mysteries, from the quantum foam to the cosmic web. So, if you haven't already, please subscribe and hit the notification bell so you don't miss our next journey to the edge of understanding. Thank you for embarking on this incredible voyage through the hidden architecture of everything. Keep asking big questions, keep challenging assumptions, and never stop looking up at the sky. Not just at the stars you can see, but at the infinite, invisible depths